On the 19th of October 2017, a telescope perched on the summit of Haleakala in Maui captured a faint smudge of light that should not have been there. It was small, it was fast, and it was not orbiting the sun, it was passing through. Not circling back, not captured by gravity, not following any arc that any asteroid, any comet, any chunk of rock or ice in our entire solar system has ever taken in the billions of years since the planets first formed. This object came from somewhere else, somewhere outside, somewhere in the dark, frozen emptiness between the stars, a place so vast and so vacant that nothing should survive the crossing. And yet, something did. Without warning, without announcement, it had entered our solar neighborhood on a trajectory that would carry it straight back out into the void. Within weeks, it would be gone forever, beyond the reach of every telescope on Earth and every satellite in orbit. And in the heartbreakingly brief window that scientists had to study it, everything they found made the mystery deeper, stranger, and more disturbing than anyone was prepared to handle. They named it Oumuamua. In Hawaiian, the word roughly translates to a messenger from afar arriving first, and the name was perfect, because that is exactly what it was. The first confirmed interstellar object ever detected passing through our solar system. Not a local comet born in the icy fringes of the Oort cloud, not a stray asteroid nudged loose from the belt between Mars and Jupiter. This was something from outside everything we know. It had travelled through the void between stars for perhaps hundreds of millions of years before its path happened to cross ours. The fact that we caught it at all was a miracle of timing, technology, and sheer blind luck. But luck in this case brought confusion. The object was tumbling end over end, completing one rotation roughly every 7 to 8 hours. As it spun, its brightness changed dramatically, far more dramatically than any known asteroid or comet. When astronomers plotted its light curve, the pattern told a deeply unsettling story about its shape. The brightness varied by a factor of approximately 10. That meant the object was either extraordinarily elongated, perhaps 10 times longer than it was wide, or extraordinarily flat, like a disc or pancake, catching the light of the sun on one broad face, and then turning to present only a thin edge. Nothing in our entire catalogue of solar system objects looked like that. Not one body, out of hundreds of thousands documented over decades of observation, even approached those proportions. Its surface was dark, deep reddish dark, coated in what appeared to be a thick crust of radiation-baked material, the result of millions of years spent exposed to the cosmic rays that permeate interstellar space. That surface told scientists almost nothing about what lay beneath it. It was a mask, an armor of accumulated damage, and behind it, the true composition of Oumuamua remained completely hidden. But the most unsettling feature was not the shape, it was not the color, it was the way it moved. As Oumuamua swung around the sun and began heading back toward interstellar space, it accelerated, not by the amount gravity alone could explain. Something else was pushing it, something invisible, something that left no trace at all. Comets do this routinely when they vent gas near the sun, but Oumuamua showed none of the expected signs. No tail, no coma, no gas, no dust, nothing. Just a dark, silent, impossibly shaped object, speeding up as it left us, heading back toward the stars for reasons no one could explain. That contradiction detonated across the scientific world. Most astrophysicists scrambled for a natural explanation. A few, led by one of the most prominent astronomers at Harvard University, proposed something far more radical. Avi Loeb, then chair of Harvard's astronomy department, suggested that the simplest explanation was that Oumuamua was not a natural object at all. It was, he argued, a piece of alien technology, a light sail perhaps, thin and flat and pushed gently by the pressure of sunlight itself. The claim was explosive, it was ridiculed by many and debated by more, and it was never fully resolved, because Oumuamua was already gone. By the time the full scope of its strangeness became clear, the object had faded beyond the reach of our most powerful instruments. It is out there still, somewhere in the dark between stars, carrying its secrets with it, growing fainter with every passing day. We will almost certainly never see it again. That is what makes this story unlike any other mystery in modern astronomy. There is no second chance, no follow-up observation, no sample return mission. Oumuamua came, baffled us, and left. and the questions it raised about its nature, its origin, and what it means for the question of whether we are alone in this galaxy have only grown louder and more urgent in the years since its departure. By the end of tonight, you are going to understand what Oumuamua actually was, or at least what the best science available tells us it might have been. You are going to hear the arguments from both sides. The astrophysicists, who insist it was natural, and the astronomer who insists it was not. You are going to see the evidence, the contradictions, and the profound implications of each answer. And you are going to confront a question that science has not yet settled and may never settle with certainty. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To truly grasp why the discovery of Oumuamua sent shockwaves through astronomy, you need to understand two things. First, the staggering, mind-breaking vastness of the space between stars, not in the abstract way that textbooks describe it, but in the visceral, physical way that makes you realize how miraculous it is that anything ever crosses that emptiness at all. And second, you need to understand what scientists expected an interstellar visitor to look like, because the gap between expectation and reality is where the entire mystery lives. Start with distance. The nearest star to our Sun is Proxima Centauri, a dim red dwarf sitting roughly 4.2 light-years away. That number sounds manageable. You can say it in under a second, but the physical distance it represents is almost impossible for the human brain to hold. That number sounds manageable. You can say it in under a second, but the physical distance it represents is almost impossible for the human brain to hold. Light, the fastest thing in the known universe, travels at approximately 299,792 kilometers per second. That is fast enough to circle the Earth more than 7 times in a single heartbeat. A beam of light leaving the Sun right now could reach the Moon in about 1.3 seconds. It could reach Mars in a few minutes. It could cross the entire diameter of the solar system in roughly 11 hours. But to reach Proxima Centauri, the nearest star, that same beam of light would need to travel continuously for 4 years and 3 months, without slowing, without stopping, at 300,000 kilometers every single second. Now try to feel that distance in more human terms. If you could build a car that somehow worked in the vacuum of space and drove at highway speed, say 100 kilometers per hour, the trip to Proxima Centauri would take approximately 45 million years. 45 million years of non-stop driving. That is longer than the time since the asteroid impact that ended the age of the dinosaurs. It encompasses the entire evolution of modern mammals, the rise and fall of countless species, the reshaping of continents by plate tectonics. All of that time compressed into a single road trip, and you would only just be arriving at the closest star, not the center of the galaxy, not the nearest spiral arm, just the nearest individual star. If you could somehow shrink the Sun down to the size of a basketball and place it in Cairo, then at the correct scale, Proxima Centauri would be another basketball sitting in Kyiv, roughly 2,500 kilometers away. And everything between those two basketballs would be empty, not merely sparse, empty, no gas stations, no landmarks, no waypoints, just void, black, frigid, silent space, with nothing in it but a few scattered atoms of hydrogen drifting through every cubic centimeter. That is the interstellar medium. That is what Oumuamua crossed. For millions of years, in the dark, alone, and yet objects cross these distances, not quickly, not intentionally, but they do. For decades, theoretical astrophysicists had predicted that the space between stars should contain solid bodies, debris ejected from other solar systems during the violent process of planet formation. When a new star forms from a collapsing cloud of gas and dust, the material around it does not settle peacefully into orbits. It crashes together, it fragments, it clumps. Small bodies called planetesimals grow by sweeping up surrounding material, and some grow large enough to become planets. But the process is chaotic and incredibly wasteful. A small body drifting too close to a forming gas giant receives a gravitational slingshot that hurls it outward, beyond the reach of its home star, onto a one-way trip into the interstellar void. It never comes back. It becomes a wanderer, belonging to no system, orbiting no star, drifting through the galaxy on a journey that can last billions of years. Our own solar system did this on a colossal scale during the first few 100 million years after the Sun ignited, roughly 4.6 billion years ago. The gravitational influence of Jupiter, Saturn, Uranus, and Neptune ejected an estimated trillions of small bodies into interstellar space. Not millions, not billions, trillions, rocky fragments from the inner system, icy planetesimals from beyond the snowline, cometary nuclei rich in water ice, frozen carbon dioxide and ammonia, all flung outward like sparks from a grinding wheel, scattered in every direction, each one beginning a journey measured in billions of years. Some of those ejected objects are still out there now, still drifting, still carrying within them the chemical fingerprint of a young solar system that has aged beyond all recognition. And if our solar system ejected trillions of objects during its formation, then presumably every solar system in the Milky Way did the same. There are roughly 200 billion stars in our galaxy, many of them formed with planetary systems. Each of those systems likely went through a similar phase of violent restructuring, flinging its own population of small bodies into the void. Multiply the trillions from each system by the hundreds of billions of systems in the galaxy, and the implication is almost beyond comprehension. Interstellar space should be filled with wandering debris, a vast, invisible population of orphaned bodies numbering in the quintillions or beyond, drifting through the galaxy like dust motes in an empty cathedral. Too small to see, too dark to detect, too numerous to count, but there. Several theoretical models attempted to pin down how many of these interstellar wanderers should pass through our solar system at any given time. Some estimates suggested that at any moment, there could be one interstellar object per cubic astronomical unit of space near the Sun. Others placed the density lower, but the consensus was firm. They were out there, and sooner or later, with the right instruments, humanity would catch one passing through. The search had been going on, quietly, for decades. As early as the 1970s, astronomers began looking for signs of interstellar interlopers among the catalogues of known comets and asteroids. The method was simple in principle. Examine the orbits of every known small body, and check whether any had a hyperbolic trajectory that could not be explained by gravitational interactions within the solar system. An object on a truly hyperbolic orbit, one with an eccentricity significantly greater than 1 and a velocity at infinity that was clearly positive, would be a candidate. But the data was ambiguous. Cometary orbits are perturbed by outgassing, by encounters with planets, and by measurement uncertainties. A comet that appeared to be on a slightly hyperbolic orbit might simply have been a solar system native whose trajectory had been nudged into a marginally unbound path by a close approach to Jupiter. No credible interstellar candidate was identified through this retrospective search. The problem was partly observational and partly conceptual. Interstellar objects were expected to be small, dark, and fast. They would approach from random directions, unlike solar system comets, which tend to come from the Oort cloud in the outer reaches of the Sun's gravitational domain. They would be on open trajectories, passing through once and never returning. And they would be faint, because their surfaces, exposed to the harsh radiation of interstellar space for millions or billions of years, would be dark, absorbing most of the sunlight that struck them, rather than reflecting it. Finding such objects required wide-field surveys that observed the sky repeatedly, compared images to detect moving objects, and had the sensitivity to spot faint, fast-moving targets against a cluttered background of stars, galaxies, and solar system bodies. These capabilities did not exist until the 21st century. The Catalina Sky Survey, the Lincoln Near-Earth Asteroid Research Project, and especially Pan-STARRS brought the combination of wide fields, deep sensitivity, and automated detection that made the discovery possible. Even so, the predicted detection rate was low. Most estimates suggested that with the technology available in the 2010s, humanity might detect one interstellar object per decade at best, and only if the population density was at the higher end of theoretical predictions. The fact that the first detection came in 2017, only a few years after the most capable surveys became fully operational, was either extraordinary luck or evidence that the interstellar population was denser than most models had assumed. It turned out to be both. The instrument that caught it was Pan-STARRS. The Panoramic Survey Telescope and Rapid Response System, operated by the University of Hawaii, sits on the summit of Haleakala on Maui, at an elevation of roughly 3,000 meters. Pan-STARRS was built for planetary defense. Its job was to find potentially hazardous asteroids and comets that might collide with Earth. It photographs the sky with a 1.4 billion pixel camera, one of the most powerful wide-field astronomical cameras ever built, and compares images from different nights to flag anything that has moved. On a clear October night in 2017, it flagged something extraordinary. Robert Werrick, a postdoctoral researcher, was reviewing Pan-STARRS data when he spotted a faint point of light that had shifted between frames. Moving objects are routine in Pan-STARRS data, but when Werrick computed this object's trajectory, the result made him pause and recheck his calculations. The object was moving too fast. Its hyperbolic excess velocity, the speed it carried above and beyond what the sun's gravity could explain, was approximately 26 kilometers per second. That translates to about 94,000 kilometers per hour of extra speed, velocity, that had nothing to do with our solar system. The object had brought that speed with it from outside. It had been carrying that momentum unchanged for an inconceivable span of time. There was only one interpretation. This object had not originated in our solar system. It had been traveling through interstellar space, entered the sun's gravitational domain, swung around on an open hyperbolic trajectory, and was now heading back out. It was a visitor from another part of the galaxy, and it was the first one ever identified in the history of human astronomy. The scientific community mobilized with extraordinary speed. Within days, observatories around the world and in space redirected their instruments toward the fading point of light. The European Southern Observatory's Very Large Telescope in Chile, with its four 8.2-meter mirrors, tracked it. The Gemini Observatory in Hawaii gathered infrared data. The Canada-France-Hawaii Telescope contributed photometry. The Hubble Space Telescope was pulled from its scheduled observations and aimed at the retreating object. The Spitzer Space Telescope, which observes in the thermal infrared, was tasked with searching for the heat signature of outgassing, the sublimation of ice that creates cometary tails. Even the Green Bank Telescope, one of the world's largest single-dish radio telescopes, listened for artificial radio signals, because that possibility, however remote, could not responsibly be ignored. The Breakthrough Listen initiative, funded by Yuri Milner, also observed. The response was global, immediate, and driven by a shared understanding that this was a once-in-a-generation event that was already slipping away with every passing hour. The trajectory was reconstructed with impressive precision. Oumuamua had entered the solar system from a direction near the constellation Lyra, close to the solar apex, the point in the sky toward which the sun itself moves through the local stellar neighborhood. Its velocity relative to the local standard of rest, the average motion of nearby stars, was about 26 kilometers per second. This was notable because it was close to the typical speed of stars in the sun's neighborhood. Oumuamua was not screaming through the galaxy at extraordinary velocity. It was drifting, coasting on ancient momentum, moving at roughly the pace of the general stellar population. It had probably been doing so for millions upon millions of years, perhaps far longer, carried by nothing but the momentum of whatever event had launched it. The direction of approach was analyzed extensively for clues about Oumuamua's origin. Researchers traced the trajectory backward, asking which stars the object might have passed near in the past. The answer was frustrating. Oumuamua's velocity, relative to the local standard of rest, was unusually low, close to the median motion of local stars, but matching no specific known star system within the traceable past. Several candidate parent systems were proposed and subsequently rejected as the trajectory was refined. The object appeared to have been drifting for so long that any connection to a specific home star was lost in the uncertainties of galactic dynamics. Stars move. Their orbits around the galactic center shift over millions of years. An object ejected from a planetary system 10 million years ago or 100 million years ago would have traveled so far and passed through so many shifting stellar neighborhoods that tracing it back to a specific origin star would require a precision in galactic kinematics that does not yet exist. This anonymity of origin added to the mystery. We could not say where Oumuamua came from. We could not identify the type of star that had formed it, or the kind of planetary system that had ejected it. All we could say was that it had been traveling for a very long time, through very empty space, before the sun's gravity bent its path and brought it briefly into the light. The approach direction near the solar apex carried a subtle statistical implication. Objects drifting slowly through the local stellar environment, relative to the sun, are more likely to be encountered from the direction the sun is moving toward, for the same reason that a driver in a rainstorm sees more raindrops hitting the windshield than the rear window. The sun is ploughing through the local cloud of interstellar debris, and objects that are nearly stationary relative to the average stellar motion will appear to come preferentially from the direction of the sun's motion. This was consistent with Oumuamua being a member of a kinematically cold population, a population of objects drifting gently through the galaxy with low random velocities, rather than a high-speed projectile from a violent ejection event. It was moving slowly, or rather, the galaxy was moving around it, while it drifted almost motionless in the galactic frame. The object reached perihelion, its closest approach to the Sun, on September 9, 2017, passing within 0.25 astronomical units, well inside the orbit of Mercury. At that distance, its sunlit surface would have been heated to several hundred degrees Celsius. For any body containing volatile ices, that proximity should produce dramatic outgassing, water ice sublimating furiously, carbon dioxide and carbon monoxide erupting into space, a bright coma blooming around the nucleus, a dust tail streaming behind in the solar wind. These are the universal signatures of a comet, and they are impossible to miss at that distance with modern instruments. Remember this. It is the central fact around which the entire debate will turn. 5 days after perihelion, Oumuamua made its closest approach to Earth's orbit on October 14th, passing within about 0.16 astronomical units, roughly 24 million kilometers, about 60 times the Earth-Moon distance. By October 19th, when Werik detected it, the object was already heading outward at high speed. Every hour that passed reduced the amount of light reaching our telescopes. The observing window was measured not in months but in weeks. Whatever could be learned about this object had to be learned now, because there would be no second opportunity. Ever. The International Astronomical Union designated it 1I/2017 U1, creating for the first time in history a naming category for interstellar objects. Then it received the Hawaiian name Oumuamua, with the okina, the glottal stop, at the beginning. The word was translated variously as scout, first distant messenger, or simply a visitor from afar arriving first. The naming was the easy part. Everything that came after was hard. The photometric data arrived first, and it was immediately strange. As Oumuamua tumbled through space, its brightness varied by a factor of roughly 10 over a rotation period of about 7 to 8 hours. To understand the significance, consider how light curves work. A perfectly spherical body shows no brightness change as it rotates, because it always presents the same cross-section to the observer. A modestly elongated body, like a potato or a lumpy rock, might vary by a factor of 1.5 to 2. The most elongated well-known asteroid in our solar system, a near-Earth object called Geographos, has an axial ratio of about 2.6 to 1 and was considered extreme by solar system standards. Oumuamua's brightness ratio of 10 implied a shape with an axial ratio of at least 6 to 1 and possibly as high as 10 to 1. If it was cigar-shaped, the inferred dimensions were roughly 230 meters long by about 35 meters wide. If it was disc-shaped, a possibility raised by later analyses, it might have been roughly 115 meters across, but astonishingly thin. Either way, the shape was completely unprecedented. No object in the catalogues of hundreds of thousands of known asteroids and comets came remotely close to those proportions. This shape problem was not merely surprising, it was theoretically troubling. The natural processes that form small bodies in space, collisions, gravitational accretion, tidal stretching, rotational breakup, do not produce objects with axial ratios above about 3 or 4 to 1 except under very unusual circumstances. Getting to 6 or 10 to 1 requires invoking exotic formation scenarios that had never been observed in any solar system. On its own, the shape would have made Oumuamua the most unusual celestial body ever detected. But the shape was only the first anomaly. Spectral observations showed a uniformly dark, reddish surface. The albedo was estimated at roughly 4 to 6%, meaning the object absorbed well over 90% of all light that struck it. This colouring was consistent with what planetary scientists call an irradiation mantle, a surface layer chemically altered by millions or billions of years of exposure to galactic cosmic rays and ultraviolet radiation in interstellar space. High-energy particles slowly strip away lighter elements and rearrange molecular bonds, leaving behind a darkened crust of complex carbon-bearing compounds. This mantle was essentially a radiation burn baked into the surface over geological timescales, and it was opaque. It revealed nothing about the interior composition. Whatever Oumuamua was made of on the inside, the outside was a featureless shell of irradiated material. Then came the critical test, the one observation that should have settled the most basic question about Oumuamua. Was it a comet, rich in volatile ices, or a rocky asteroid with no ices at all? The answer lay in outgassing. When a comet approaches the Sun, its ices sublimate, transitioning from solid to gas, and that gas escapes the surface in jets. These jets carry tiny dust particles with them, forming the fuzzy coma that surrounds the nucleus and the long, luminous tail that streams behind it in the solar wind. At the distance Oumuamua reached from the Sun, well inside Mercury's orbit, any cometary body should have been outgassing vigorously. The signatures should have been unmistakable. The Spitzer Space Telescope observed Oumuamua in the thermal infrared, the wavelength range most sensitive to emission from carbon dioxide and carbon monoxide gas. It detected nothing. Spitzer placed strict upper limits on the production rates of these gases, limits that would become pivotal evidence in the debates that followed. Hubble observed invisible light, searching for the scattered glow of a dust coma. It found nothing. Ground-based spectroscopy searched for emission lines from water vapor, cyanogen, and other common cometary molecules. Nothing. Every instrument, every wavelength, every technique designed to detect cometary activity returned the same answer: silence. Oumuamua appeared completely inert, dead, despite having been roasted by the sun, at a distance where any normal comet would be dramatically active. For a rocky asteroid with no volatile content, that silence would be entirely expected. An asteroid has no ices to sublimate, so of course there would be no outgassing. If Oumuamua were simply an interstellar chunk of dry rock, the story would have been surprising because of the shape, but otherwise straightforward. But in June of 2018, the story became anything but straightforward. Marco Micheli, an astronomer at the European Space Agency, led a team that published a paper in the journal Nature that would become the single most debated observational result of the entire Oumuamua saga. The team had combined astrometric data from Hubble with ground-based tracking from multiple observatories to determine Oumuamua's trajectory with extraordinary precision over a span of several months. What they found was a deviation, tiny but unmistakable. Oumuamua was not following the path that gravity alone would dictate. It was accelerating, being pushed by something. The additional acceleration was small, on the order of 5/millionths of a meter per second squared. But it was real, and it was statistically significant beyond any reasonable doubt. The paper was meticulous in ruling out alternative explanations. Solar radiation pressure acting on a body of normal proportions was too weak by roughly an order of magnitude. Solar wind drag was negligible. Interactions with the interplanetary magnetic field were irrelevant at Oumuamua's size and composition. Yarkovsky and Yorp effects, the subtle forces caused by uneven thermal radiation from a spinning body, were far too small. The only conventional mechanism that could produce enough force to account for the observed acceleration was cometary outgassing, the jet engine effect of sublimating ice pushing the body in the opposite direction. But there was no gas. That single sentence, that single contradiction, is the fault line on which the entire scientific debate about Oumuamua rests. Acceleration implies a force. The only known force strong enough is outgassing. But every search for outgassing found nothing. Either the gas was there but invisible, or something else was providing the push. And each of those possibilities led down a very different path, one of them natural but challenging, and the other extraordinary, in a way that most scientists were deeply reluctant to contemplate. But before the battle over interpretation could begin in earnest, there is one more piece of context that matters enormously. The discovery of Oumuamua did not happen in a vacuum. It happened at a specific moment in the history of astronomy, a moment when the tools to detect such objects had only barely become powerful enough. Pan-STARRS had been fully operational for just a few years. The survey techniques were still being refined, and the object was found not on its way in, not at its closest approach, but already on its way out. It had already swung around the Sun and made its closest pass to Earth by the time Werik flagged it. If Pan-STARRS had been slightly less sensitive, or if the weather on Maui had been poor that night, or if the trajectory had passed through a part of the sky the telescope was not scanning, we would have missed it entirely. It would have passed through our solar system undetected, a ghost that came and went without leaving a trace. This near-miss quality of the discovery haunted astronomers. It raised an uncomfortable question. How many interstellar objects had already passed through the solar system without being noticed? The answer, almost certainly, was a very large number. Models suggested that interstellar objects may cross the inner solar system within Jupiter's orbit multiple times per year. Most would be too small, too dark, or too fast to detect with current technology. Pan-STARRS caught Oumuamua partly through capability and largely through fortune. The object was on the larger end of what theory predicted, roughly 100 to 200 meters in its longest dimension, and it passed close enough to the Sun and Earth to reflect enough light for detection. A smaller object, or one on a wider trajectory, would have been invisible. This realization carried a profound implication. The density of interstellar objects in our neighborhood was probably much higher than most earlier estimates had assumed. If we had caught one within just a few years of Pan-STARRS becoming fully operational, the underlying population had to be vast. Some revised calculations suggested roughly one interstellar object per cubic astronomical unit of space near the Sun at any given time. That is a density far greater than earlier theoretical work had predicted. It meant the galaxy was more prolific at scattering debris between stars than anyone had appreciated, and it set the stage for a stunning confirmation. Less than 2 years after Oumuamua's detection on August 30th, 2019, an amateur astronomer named Gennady Borisov, working with a home-built telescope from an observatory in Crimea, discovered the second interstellar object, Comet 2I/Borisov. Unlike Oumuamua, Borisov was immediately and unmistakably a comet. It had a bright coma, it had a dust tail. Spectroscopic analysis revealed water vapor, carbon monoxide, and other familiar cometary molecules. It was in every way a perfectly normal comet except for one extraordinary detail. Its trajectory was hyperbolic and unambiguously interstellar. It came from outside the solar system, swung through and departed. Borisov was exactly what scientists had always expected an interstellar comet to look like. It was reassuring, it was comprehensible, and it made Oumuamua's strangeness all the more glaring. If interstellar comets look like Borisov, then what was Oumuamua? It behaved like neither a comet nor an asteroid. It occupied a strange, uncomfortable middle ground, exhibiting properties that contradicted every known category of celestial object. It was an outlier not only among solar system bodies, but among the very population of interstellar wanderers it was supposed to belong to. 2 interstellar objects found within 2 years. One perfectly normal, one profoundly abnormal. The contrast sharpened every question and made the stakes impossibly clear. The foundation was complete. The most unprecedented object in the history of astronomy had revealed itself, and it had left behind more questions than answers. Its shape was wrong. Its surface was opaque. Its trajectory was impossible to explain with gravity alone. And the only standard mechanism that could account for its anomalous acceleration was contradicted by every observation designed to detect it. The battle over what Oumuamua actually was had only just begun, and the first shot would be fired from an office at Harvard University. The core problem with Oumuamua was not any single anomaly. It was the convergence of all of them at once, on a single object, at a moment in history when there was no possibility of gathering more data. Take the shape on its own, unusual, but perhaps not impossible, given the vast diversity of objects in the universe. Take the lack of outgassing on its own, puzzling, but perhaps the volatiles were buried too deep, or were of a type that our instruments could not detect. Take the anomalous acceleration on its own, surprising, but non-gravitational forces act on comets routinely. Each anomaly, considered in isolation, could be stretched to fit within known frameworks. But stack them together, a shape unlike anything ever catalogued, a surface that revealed nothing, an acceleration that demanded outgassing, an outgassing that was nowhere to be found, on an object that had come from beyond the solar system and was already disappearing into the void. And the combination became something that science had no ready answer for. The shape was the first battleground. When researchers analyzed Oumuamua's light curve, the brightness variation of roughly 10:1 forced them to confront a geometry that had no precedent in solar system science. If the object was elongated, cigar-shaped, it had to be at least 6 times longer than it was wide, possibly 10 times. If instead it was flat, disc-shaped, it had to be extremely thin relative to its width. Both interpretations were published, both were debated, and both led into uncomfortable territory. For the cigar-shape interpretation, the challenge was formation. Natural processes that create small bodies in space, collisions, fragmentation, gravitational accretion, tend to produce roughly spheroidal objects with modest elongation. Ratios above 3 or 4:1 are rare, and ratios of 6 to 10:1 are essentially unheard of. Tidal forces from close encounters with stars can stretch bodies, but producing such extreme elongation in an object of Oumuamua's size would require conditions that were difficult to arrange in any standard astrophysical scenario. The cigar shape was theoretically possible, but it sat at the extreme edge of plausibility, demanding special circumstances that had not been observed or modelled before. The disc shape interpretation was, if anything, more troubling. In 2019, researchers showed that a thin, oblate ellipsoid, viewed tumbling along certain axes, could produce the same light curve as a cigar. A disc-shaped Oumuamua would explain the brightness variation just as well. But thin, flat discs do not form naturally in any known planetary process. You do not get pancakes from collisions. You do not get membranes from gravitational accretion. A flat disc suggested either a formation mechanism that no one had identified, or something else entirely. The rotation itself added another layer of complexity. Oumuamua was tumbling, not spinning smoothly around a single axis. Its rotation was non-principal axis, meaning it was wobbling and precessing in a complicated pattern. This tumbling state was significant because it contained information about the object's history. A body that forms in a spinning disk or is ejected cleanly from a planetary system typically rotates around its shortest axis, the state of minimum rotational energy. A tumbling body has been disturbed, kicked into an excited rotational state by some event, perhaps a collision, a tidal encounter, or the talks of asymmetric outgassing. The timescale for a body of Oumuamua's size to return to principal axis rotation through internal energy dissipation depends on its composition and structure. For a solid, monolithic rock, the damping timescale could be billions of years, meaning the tumbling could be primordial. For a loosely bound rubble pile, the timescale would be much shorter, and the tumbling would imply a relatively recent disturbance. The tumbling rate was measured at roughly 7 to 8 hours per full cycle. This was not especially fast, well below the spin barrier limit, where centrifugal forces would tear apart a loosely bound body. But combined with the extreme elongation, it created a peculiar picture, an object shaped like a cigar or a disc, tumbling end over end every 7 hours, hurtling through the solar system at tens of kilometers per second, showing no signs of cometary activity despite having been roasted by the sun, and inexplicably accelerating. Each property alone was notable. Together, they formed a pattern that resisted every simple explanation. The acceleration deserves special emphasis because it was the single most consequential observation in the entire Oumuamua dataset. Without the acceleration, the object would have been classified as an interstellar asteroid, extraordinary in its shape and origin, but ultimately comprehensible within existing frameworks. The acceleration changed everything. It demanded a physical mechanism, a force beyond gravity that was pushing the object. And in solar system science, there is only one known mechanism that routinely produces non-gravitational accelerations on small bodies: the rocket effect of sublimating ice. The way this works is straightforward. When a comet approaches the Sun, its ices sublimate, turning from solid to gas. The gas escapes the surface at high velocity, typically hundreds of meters per second. By Newton's third law, the escaping gas exerts an equal and opposite force on the nucleus. This is the same principle that propels a rocket. The effect is small for any single molecule, but when billions of tons of ice sublimate over weeks or months, the cumulative thrust can measurably alter the comet's trajectory. This non-gravitational acceleration has been observed and precisely measured for dozens of solar system comets. The physics is uncontroversial, but the physics requires gas. Visible, detectable, measurable gas. The rocket effect cannot operate silently. Gas must leave the surface, and that gas can be detected either directly, through spectroscopy of its emission lines, or indirectly, through the dust it drags along, the coma it creates, or the torques it imparts on the nucleus. For every known comet that exhibits non-gravitational acceleration, the outgassing is confirmed by multiple independent observations. There are no exceptions in the solar system's catalogue of comets. Non-gravitational acceleration and detectable outgassing go hand in hand until Oumuamua, and it gets worse. The magnitude of the acceleration placed additional constraints on the problem. The observed acceleration was not constant. It varied with distance from the Sun, in a way that was broadly consistent with a sublimation-driven force, falling off as the object moved farther from the Sun and the heating decreased. This was tantalizingly similar to the pattern seen in normal comets. It suggested that whatever was causing the push was solar-driven, related to the energy input from sunlight. This narrowed the field of possible explanations, because it ruled out mechanisms that were distance-independent, like the gradual release of stored internal energy, or the slow disintegration of a structurally weak body. The distance dependence pointed towards solar radiation as the energy source, but the two known ways that solar radiation can push a body, radiation pressure and thermally driven outgassing, both had problems. Radiation pressure was too weak, by roughly an order of magnitude, for a body of normal density and proportions. It only worked if the object was extraordinarily thin and light, which was the path that led to the light sail hypothesis. Outgassing explained the acceleration quantitatively, but was contradicted by the non-detections. The two mechanisms bookended the problem, each explaining some aspects and failing at others, leaving Oumuamua in a no-man's land between them. It was this something else that Avi Loeb seized upon. In November of 2018, Loeb and his postdoctoral researcher, Shmuel Bialy, published a paper in the Astrophysical Journal Letters that would become the most controversial scientific paper of the decade. Their argument was deceptively simple. If Oumuamua was a thin, flat object, a disk with a very high ratio of surface area to mass, then the anomalous acceleration could be entirely explained by a well-understood physical effect: solar radiation pressure. Photons from the Sun carry momentum. When they strike a surface, they exert a tiny push. For most objects, this push is negligible compared to gravity. But for an object that is extremely thin and extremely lightweight, essentially a sheet of material with a very large area and very little mass, the radiation pressure becomes significant. It can accelerate the object measurably. The math is striking. Bialy and Loeb calculated that if Oumuamua had a thickness of approximately 0.3 to 0.9 millimeters, solar radiation pressure alone would produce an acceleration matching what Micheli's team had measured. Less than a millimeter thick, thinner than a credit card, thinner, in some estimates, than a few sheets of paper stacked together. At the inferred dimensions of the object, if disc-shaped, roughly 100 meters across, such a structure would be essentially a membrane, a sail, and that word was not chosen casually. Light sails are real technology. They are not science fiction. Japan's space agency, JAXA, successfully deployed a solar sail called Icaros in 2010, demonstrating that a thin reflective membrane could be accelerated by sunlight in space. The Planetary Society launched LightSail 2 in 2019, a small spacecraft propelled entirely by solar radiation pressure, and the most ambitious light sail project of all, the Breakthrough Starshot Initiative, funded by Yuri Milner and publicly supported by the late Stephen Hawking, aims to use powerful Earth-based lasers to accelerate ultra-thin, ultralight sails to 20% of the speed of light, fast enough to reach Proxima Centauri within about 20 years. Light sails are not theoretical. They are under active development. They represent, in the view of many physicists, the most plausible technology for interstellar travel. Loeb's proposition was direct. Oumuamua's shape, its acceleration, and its lack of outgassing were all consistent with a single simple hypothesis. The object was a light sail, either a functional one, perhaps a probe, or a defunct one, a piece of discarded or damaged technology drifting through the galaxy like a piece of space junk, a cosmic artifact, evidence that somewhere, sometime, in the vast history of the Milky Way, a civilization had built a light sail and launched it into the void, and it had drifted, pushed by starlight and stellar winds until its path happened to cross ours. The reaction was immediate and intense. Within days, the paper was international news. Headlines screamed about Harvard professors claiming that aliens had sent an object through the solar system. Talk shows and podcasts ran breathless segments, and the vast majority of the astronomical community pushed back with force. The objections were professional, methodical, and sometimes personal. The scientific criticism came on multiple fronts. First, Loeb's paper was not wrong in its physics. The mathematics of radiation pressure on a thin membrane were correct. The problem, critics argued, was the reasoning. The paper had demonstrated that a light sail could explain the observations. It had not demonstrated that a light sail was the best explanation, or even a likely one. In science, the fact that a hypothesis is consistent with data is necessary but not sufficient. Many hypotheses can be consistent with limited data. What matters is whether the hypothesis is the simplest, the most parsimonious, the one that requires the fewest extraordinary assumptions. And an artificial light sail built by an extraterrestrial civilization was by any measure the most extraordinary assumption on the table. This is the heart of Occam's razor as applied to science. Do not multiply entities beyond necessity. If a natural explanation exists that can account for the observations, it should be preferred over an artificial one, because natural explanations rest on known physics and observed phenomena, while artificial explanations require invoking an entire civilization, its motivations, its technology, and its proximity, none of which have been independently confirmed. Loeb countered that Occam's razor should not be used to exclude hypotheses that are uncomfortable, and that limiting the search space to natural explanations was itself a form of bias. The debate became as much about the philosophy of science as it was about the physics. The second wave of criticism was more pointed. Researchers noted that Loeb had not published his argument as a peer-reviewed research paper first, and then discussed it publicly. Instead, the paper and the publicity arrived almost simultaneously, a pattern more typical of advocacy than of scientific inquiry. Some colleagues accused Loeb of seeking attention. Others were more generous, suggesting that the hypothesis was worth publishing precisely because it was so provocative and because no natural explanation had yet succeeded in accounting for all of Oumuamua's anomalies simultaneously. But the damage to collegial relations was real and lasting. Loeb's standing in parts of the astronomical community shifted from respected theorist to polarizing figure within a matter of weeks. And yet, beneath the controversy, there was a genuine scientific crisis that had nothing to do with Loeb personally. Natural explanations for Oumuamua's acceleration were struggling. Every proposed mechanism had a problem, and the race to find one that worked would consume the astrophysics community for years. The first and most obvious natural explanation was the one Micheli's team had already proposed: invisible outgassing. Perhaps Oumuamua was a comet after all, but one that produced gas in a form that existing instruments could not detect. The Spitzer telescope had placed strict upper limits on carbon dioxide and carbon monoxide outgassing. Hubble had found no dust coma. Ground-based spectroscopy had detected no water vapor. But what if the gas being released was something else? What if it was pure molecular hydrogen, or some other species with no strong emission lines in accessible wavelengths? The problem with this hypothesis was quantitative. To produce the observed acceleration, a substantial amount of mass had to leave the surface. Estimates suggested that Oumuamua would need to lose roughly 10% of its total mass during the perihelion passage. That is an enormous amount of outgassing. Even if the gas itself were invisible, the sheer volume of material leaving the surface should produce observable secondary effects. Scattering of sunlight by released dust particles, changes in the rotation rate, due to torques from asymmetric jets, perhaps even fragmentation of the body under the stress. None of these secondary effects were observed. Oumuamua's rotation was stable. Its brightness varied smoothly. There was no dust. There was no disruption. Whatever was pushing it was doing so cleanly, uniformly, and without any visible byproduct. In 2019, Daryl Seligman and Gregory Laughlin proposed a hypothesis that was ingenious in its simplicity. What if Oumuamua was made primarily of molecular hydrogen ice? Hydrogen is the most abundant element in the universe. In the coldest regions of interstellar space, far from any star, temperatures drop to just a few degrees above absolute zero, cold enough for hydrogen gas to freeze into a solid. A body made of hydrogen ice would be extraordinarily volatile. When it entered the inner solar system and was heated by the sun, the hydrogen would sublimate rapidly, producing powerful outgassing. And here was the crucial point. Molecular hydrogen has essentially no observable spectral signature in the wavelengths that had been used to search for cometary activity around Oumuamua. It would be invisible gas. The outgassing would provide the acceleration, and the lack of detected emissions would be explained simultaneously. The hypothesis was elegant. It was also immediately challenged. Thiem Huang, an astrophysicist specializing in interstellar dust and radiation, published a detailed rebuttal within months. The problem was survival. A body of pure hydrogen ice, traveling through interstellar space for millions of years, would be subjected to continuous bombardment by cosmic rays and heating by the diffuse interstellar radiation field. Even in the coldest known environments of the galaxy, these energy sources would gradually sublimate the hydrogen. Huang's calculations showed that a hydrogen iceberg of Oumuamua's size would evaporate completely long before it could travel the immense distances between stars. It would not survive the journey. To put it simply, you cannot carry a block of hydrogen ice across the galaxy for millions of years any more than you can carry a block of regular ice across the Sahara Desert for a decade. The numbers did not work. Seligman and Laughlin countered that their object might have formed relatively recently in a dense molecular cloud, perhaps one the solar system had recently passed through. If the travel time were short enough, tens of thousands of years rather than millions, a hydrogen iceberg might survive. But this introduced a new constraint. The birthplace had to be close and the object had to be young, and neither requirement was easily reconciled with Oumuamua's apparently ancient, irradiated surface. The hydrogen ice debate illuminated a broader challenge that would recur with every subsequent hypothesis: the tension between explaining Oumuamua's individual properties and explaining the implied population of objects like it. If Oumuamua was a hydrogen iceberg, then how many hydrogen icebergs must exist in interstellar space for pan-stars to have detected one within just a few years of operation? The answer was a very large number, and producing that many hydrogen icebergs required a formation mechanism that was far more prolific than any known process in molecular clouds. The individual explanation might work. The population-level accounting did not. This problem, the tension between explaining one object and explaining the population that one detection implies, would haunt every natural hypothesis proposed for Oumuamua. It is a consequence of the survey's limited sensitivity and coverage. Detecting one interstellar object in a short time window means that many more must exist below the detection threshold. Every hypothesis must not only explain the observed properties of Oumuamua, but also be consistent with a galactic population large enough to deliver one such object into our detection volume within the survey period. This is a severe constraint, and it eliminated several otherwise promising ideas. In 2021, Stephen Jackson and Alan Desch proposed an alternative, nitrogen ice. Their paper argued that Oumuamua could be a fragment of a Pluto-like body from another star system, a chunk of frozen nitrogen knocked off the surface by an impact. Nitrogen ice, like hydrogen ice, sublimates in a way that produces minimal observable signature at the wavelength searched. It is more thermally stable than hydrogen ice, so it could survive longer in interstellar space, and it would produce a non-gravitational acceleration consistent with the observations. The nitrogen ice hypothesis was clever and detailed. Jackson and Desch modeled the erosion of the body as it passed through the solar system, showing that the sublimation could sculpt an initially more rounded chunk into the extreme shape observed, essentially carving Oumuamua into a thin slab as the nitrogen boiled away from all surfaces. The shape and the acceleration were explained simultaneously. The paper was well received as a serious natural explanation. But it too had a problem, and it was a big one. The amount of nitrogen required was extraordinary. To explain the number of interstellar objects implied by Oumuamua's detection, given the limited survey coverage of pan-stars, the galaxy would need to be saturated with nitrogen ice fragments. Calculations showed that more nitrogen would need to be in the form of interstellar debris than could plausibly be produced by all the Pluto-like bodies in the galaxy over the entire age of the Milky Way. The nitrogen ice model worked beautifully for the individual object, but failed catastrophically at the population level. There simply was not enough nitrogen in the right form to make the numbers work. Then came the most recent and perhaps most promising natural hypothesis. In March of 2023, Jennifer Bergner and Daryl Seligman, the same Seligman who had proposed the hydrogen ice idea years earlier, published a paper in the journal Nature that offered a different mechanism entirely. Their proposal was that Oumuamua did not need to be made of exotic ice. It could be a perfectly ordinary body, a water ice-rich comet, but one whose ices had been chemically altered during its long journey through interstellar space. The mechanism was radiolysis. As cosmic rays penetrate the surface of an icy body over millions of years, they break water molecules apart. The oxygen atoms bond with other elements or remain in the ice matrix, but the hydrogen atoms, being tiny and mobile, diffuse through the lattice and become trapped as molecular hydrogen gas within the ice. Over millions or billions of years of interstellar travel, an enormous amount of hydrogen can accumulate inside the body's ice, stored not as hydrogen ice but as hydrogen gas bubbles suspended within water ice. When such a body approaches a star and begins to warm, the trapped hydrogen is released, not through the usual process of water-ice sublimation, but through a gentler process. As the upper layers of ice restructure and warm, the trapped gas escapes. The result is outgassing of molecular hydrogen, invisible to conventional spectroscopy, without the production of the water vapor, dust, and coma that accompany normal cometary activity. The acceleration is explained. The lack of visible outgassing is explained, and the mechanism requires nothing exotic, only ordinary water ice and a long exposure to the normal radiation environment of interstellar space. Every interstellar body with water ice should arrive in a new star system loaded with trapped hydrogen, ready to release it upon warming. Bergner and Seligman's paper was widely praised as the most parsimonious natural explanation yet offered. It did not require exotic ices. It did not require unusual formation mechanisms. It did not require invoking alien technology. It required only physics that was already well understood in laboratory settings. The elegance of the trapped hydrogen hypothesis lay in its universality. If the mechanism worked as proposed, it would not be unique to Oumuamua. Every icy body that spends a long time in interstellar space, exposed to cosmic rays, would accumulate trapped hydrogen in its water ice. The longer the exposure, the more hydrogen would build up. This meant that the first interstellar objects to be detected should, as a class, exhibit anomalous acceleration when they entered a new star system and were warmed by the host star. The mechanism predicted a systematic effect, not a one-off anomaly. That kind of prediction is exactly what makes a hypothesis scientifically powerful, because it can be tested against future detections. But there was an immediate objection. If every icy interstellar body releases trapped hydrogen upon warming, then why did Borisov, the second interstellar object, behave like a perfectly normal comet? Borisov showed conventional outgassing, a bright coma, and a dust tail. There was no evidence of anomalous behavior beyond its cometary activity. One possible answer was that Borisov was so actively outgassing in conventional ways that any trapped hydrogen release was swamped by the dominant signal. Another was that Borisov had spent less time in interstellar space and had accumulated less trapped hydrogen. A third was that the two objects had fundamentally different compositions and histories. Each answer was plausible, none was conclusive. With a sample size of 2, both members' wildly different statistical reasoning offered little guidance. The experimental side of the hypothesis was also developing, but slowly. Laboratory experiments conducted at institutions in the United States and Europe had demonstrated that proton irradiation of water ice at temperatures relevant to interstellar space does produce trapped molecular hydrogen. The physics was confirmed at the molecular level, but scaling from laboratory quantities, thin films of ice exposed to particle beams for hours or days, to the enormous volumes and timescales relevant to Oumuamua, was a leap that required careful extrapolation. The rate of hydrogen production per unit volume, per unit time was measured in the lab. Multiplying that rate by the volume of a 100-meter body and the millions of years of interstellar travel gave an estimate of the total trapped hydrogen available for release. Whether that estimate was sufficient to produce the observed acceleration depended on assumptions about the ice structure, the porosity of the body, the depth to which cosmic rays penetrate, and the efficiency with which trapped gas escapes when the ice is warmed. Each of these factors carried uncertainties, and the combined uncertainty was large enough to prevent a definitive conclusion. But it was not located. As of the time of this writing, the trapped hydrogen hypothesis has not been experimentally verified under conditions that replicate interstellar exposure. Laboratory experiments have demonstrated that cosmic ray bombardment can produce trapped hydrogen in water ice, but whether the quantities produced over astronomical timescales would be sufficient to generate the observed acceleration remains an open question. The mechanism is plausible, it may well be correct, but it has not been proven, and without Oumuamua itself available for further observation, it may never be proven directly. There is a pattern that runs through all of these attempts at explanation, and it is worth making explicit. Each hypothesis solves one or two aspects of the puzzle while creating new difficulties elsewhere. The hydrogen ice hypothesis solves the invisible outgassing problem, but fails on survival. The nitrogen ice hypothesis solves both the outgassing and the shape, but fails on population accounting. The trapped hydrogen hypothesis solves the outgassing and the population problem, but lacks experimental confirmation at scale and must contend with the Borisov counterexample. The light sail hypothesis solves everything simultaneously, but requires extraterrestrial technology. Each proposal is a trade between explanatory power and the plausibility of its assumptions, and no proposal has yet been found that maximizes both. This is not a failure of science. It is science working exactly as it should in the face of radically insufficient data. The history of astronomy is full of objects that were initially misunderstood, from the first quasars, which were initially mistaken for nearby stars, to gamma-ray bursts, which puzzled astronomers for decades before their extragalactic origin was established. In many of those cases, the resolution came not from cleverer theoretical work, but from additional observations, a new detection, a different wavelength, a closer look. Oumuamua denies us that option. But here is the problem. The object is accelerating away from us, and the window for additional observation closed years ago. Some researchers have proposed that Oumuamua might represent an entirely new category of solar system object, one that does not correspond to any previously recognized class. This idea, sometimes called the dark comet hypothesis, suggests that there may be a population of small bodies with compositions and structures that produce non-gravitational acceleration without conventional observable signatures. In the years following Oumuamua's detection, several researchers identified a handful of known solar system objects small near-Earth asteroids that also exhibited anomalous accelerations inconsistent with gravity alone and showed no evidence of cometary activity. These dark comets, as they were informally called, are poorly understood. Their existence suggests that the boundary between asteroids and comets may be less sharp than previously assumed, and that non-gravitational forces may operate on small bodies through mechanisms that are not yet fully characterized. If Oumuamua was a particularly extreme example of a dark comet, then its anomalies might be unusual in degree, but not in kind. This interpretation was attractive because it did not require exotic materials, alien technology, or unprecedented formation mechanisms. It required only the acknowledgement that the census of small body behavior in the solar system is incomplete, and that objects with unusual properties may be more common than the catalogue suggests. But it also raised a new question. What physical mechanism drives dark comets? Without understanding the force, calling the category a name did not constitute an explanation. It was a label, not a solution. This is the cruelest aspect of the entire saga. Oumuamua is gone. It passed through the solar system in a matter of weeks, and by early 2018, it had faded below the detection threshold of even the most powerful telescopes on Earth. It is now beyond the orbit of Neptune, still moving outward at roughly 26 kilometers per second, growing dimmer and more unreachable with every passing day. No spacecraft was launched to intercept it. None could have been, given the timeline and the velocities involved. There will be no follow-up observations. There will be no sample return. There will be no close-up photographs. Every question about Oumuamua's nature, composition, origin, and the cause of its anomalous acceleration must be answered using only the data collected during those few frantic weeks in late 2017 and early 2018. And that data, as rich as it is not enough to distinguish definitively between the competing hypotheses. The scientific method thrives on the ability to test, to repeat, to gather more data, to refine hypotheses against new observations. Oumuamua denied science that opportunity. It appeared, baffled every attempt at classification, and vanished. What remains is a dataset that is consistent with multiple mutually exclusive interpretations, some natural, at least one artificial, and no way to gather the additional evidence that would resolve the ambiguity. It is, in a very real sense, the perfect scientific puzzle, endlessly debatable, permanently unresolvable with existing data, and guaranteed to generate passionate disagreement for decades to come. And the disagreement had only just begun to deepen. Because the arguments about Oumuamua were not merely technical. They were revealing fractures in the way science itself handles questions that sit at the boundary between the known and the unknown, between the natural and the possibly artificial, between cautious incrementalism and bold speculation. Those fractures, and the people who stood on either side of them, are where the story turns next. Most scientific controversies resolve through the slow accumulation of evidence. Someone proposes a hypothesis, others test it, data arrives, the hypothesis is confirmed, modified, or discarded. The process takes years, sometimes decades, but it converges. The Oumuamua debate did not converge, it escalated. And it escalated not because new data arrived, but because the absence of new data created a vacuum that was filled by something science is poorly equipped to handle: competing narratives. Avi Loeb did not retreat after the initial backlash to his light sail paper. He advanced. In 2021, he published a book, Extraterrestrial: The First Sign of Intelligent Life Beyond Earth, which presented the light sail hypothesis to a general audience with considerable rhetorical skill. The book was a bestseller. It made Loeb one of the most recognized scientists in the world, for better or worse, and it deepened the rift between Loeb and much of the astronomical establishment. The book's argument was layered. At one level, it simply restated the case for considering an artificial origin. But at a deeper level, Loeb was making a sociological argument about science itself. He contended that the astronomical community's refusal to seriously consider the artificial hypothesis was not driven by evidence but by cultural conservatism, a deeply ingrained reluctance to entertain ideas that carry the stigma of science fiction. He compared the situation to historical episodes in which the scientific establishment had rejected ideas that later proved correct, drawing parallels to the resistance Galileo faced to the decades of hostility toward continental drift, to the initial dismissal of the idea that an asteroid had killed the dinosaurs. In each case, Loeb argued, the establishment had been wrong, not because it lacked data, but because it lacked imagination or courage. This argument was effective with the public and infuriating to many scientists. The comparison to Galileo, in particular, struck a nerve. Scientists pointed out that for every Galileo who was vindicated, there are thousands of contrarians whose ideas were rejected because they were genuinely wrong. The fact that the establishment is sometimes wrong does not mean that the establishment is wrong now, and comparing oneself to Galileo, even implicitly, is widely regarded within academia as a warning sign of grandiosity rather than insight. The sociological argument, whatever its merits, made the scientific discussion harder, not easier. But Loeb was also doing something that few of his critics acknowledged. He was right that the astronomical community had an institutional allergy to the subject of extraterrestrial technology. For decades, SETI, the search for extraterrestrial intelligence, had occupied an awkward position in mainstream astronomy. It was scientifically legitimate in principle but culturally marginal in practice. SETI researchers had trouble getting telescope time. SETI papers were difficult to publish in top journals. Graduate students were quietly advised that working on SETI could harm their careers. The underlying message was clear. Searching for alien civilizations was not quite respectable. It was tolerated barely, but it was not embraced. This marginalization had deep roots. The modern scientific community's discomfort with extraterrestrial intelligence stems partly from the cultural association between alien claims and pseudoscience. The UFO subculture, conspiracy theories, tabloid sensationalism. Scientists who study exoplanets or stellar evolution do not want to be associated with those fringe communities, and the simplest way to maintain distance is to avoid the topic of alien technology altogether. The result is a kind of professional self-censorship, not a conspiracy, but a collective agreement that certain questions are best left unasked in polite scientific company. Loeb's provocation forced the community to confront this self-censorship directly, and it did so at a moment when the broader cultural landscape was shifting. In 2020 and 2021, the United States government began releasing previously classified information about unidentified aerial phenomena, the rebranded term for what had previously been called UFOs. Congressional hearings were held. Military pilots testified about encounters with objects that displayed flight characteristics beyond known technology. A Pentagon report acknowledged the existence of encounters that could not be explained. The cultural stigma around discussing unidentified objects in the sky, while not eliminated, was substantially reduced. This cultural shift created a strange environment for the Oumuamua debate. Suddenly, the question of whether an interstellar object might be artificial was no longer confined to academic journals. It was part of a larger national and international conversation about unexplained phenomena, government secrecy, and humanity's place in the universe. The Oumuamua controversy became entangled with the UAP discussion, often against the wishes of the scientists involved, who saw the two topics as entirely separate. An interstellar light sail from a distant civilization, if it existed, would have nothing to do with aerial encounters near military bases. But in the public imagination, the two merged into a single narrative. The aliens might be real, and the establishment might be hiding it. This merging dismayed scientists on both sides of the Oumuamua debate. Researchers who believed Oumuamua was natural did not want to be seen as debunking alien claims alongside UFO conspiracists. Researchers who, like Loeb, thought the artificial hypothesis deserved consideration did not want their careful physical arguments lumped in with grainy cockpit videos and stories of little green men. But the entanglement was perhaps inevitable. Once the idea of extraterrestrial technology enters public discourse, it obeys the logic of public discourse, not the logic of academic seminars. Loeb responded to the escalating attention not by retreating but by institutionalizing his approach. In July of 2021, he announced the creation of the Galileo Project, a research initiative housed at Harvard, with the explicit goal of searching for physical evidence of extraterrestrial technological civilizations. The project was ambitious. It proposed building a network of optical and infrared telescopes, atmospheric sensors, and data processing pipelines to systematically monitor the sky for objects that might be artificial. It also proposed developing the capability to intercept and study future interstellar objects. Building on the lessons of Oumuamua, the project was funded entirely by private donations, bypassing the traditional grant agencies that Loeb believed would never fund such work. The Galileo project drew both excitement and skepticism. Its stated principles were scientifically sound: transparent data, peer-reviewed publications, no reliance on classified government information, no engagement with anecdotal reports. It was, at least on paper, a serious scientific effort, but critics noted that the project's framing was inherently biased toward finding artificial objects. If you build an instrument designed to detect alien technology, every anomalous reading becomes a potential alien artifact. The risk of confirmation bias was enormous, and managing that risk in a project founded on the premise that alien technology might exist was a challenge that would test even the most rigorous methodology. The Galileo project also highlighted a deeper tension in the search for extraterrestrial intelligence. For decades, the dominant paradigm in SETI had been the search for radio signals, electromagnetic broadcasts from distant civilizations. This approach, pioneered by Frank Drake in 1960 with his famous experiment at the Green Bank telescope, rested on a specific assumption: that civilizations communicate using radio waves and that those signals can be detected across interstellar distances. The Drake equation, the famous thought experiment that estimates the number of communicative civilizations in the galaxy, was built around this assumption. The Drake equation is worth pausing on, not because it provides an answer, it does not, but because it illuminates the structure of human ignorance about extraterrestrial intelligence. The equation multiplies together a series of factors: the rate of star formation, the fraction of stars with planets, the fraction of planets that develop life, the fraction of life that becomes intelligent, the fraction of intelligent species that develop detectable technology, and the average lifetime of such civilizations. When Drake first formulated the equation in 1961, most of these factors were completely unknown. Today, thanks to missions like Kepler and TESS and ground-based exoplanet surveys, the first two factors are well constrained. Stars form at a steady rate, and planets are extraordinarily common. Nearly every star in the galaxy has at least one planet. The fraction with Earth-like planets in habitable zones is somewhere around 5 to 20%. The universe is rich with potential homes for life. But the remaining factors, the ones involving the emergence of life, the development of intelligence, the creation of technology, and especially the longevity of civilizations, remain essentially unconstrained. They could be tiny, making us effectively alone, or substantial, making the galaxy teeming with civilizations. The Drake equation does not tell us how many civilizations exist. It tells us what we need to know in order to find out. The Fermi paradox sits at the intersection of the Drake equation and the vastness of the galaxy. The paradox, attributed to the physicist Enrico Fermi during a lunchtime conversation in 1950, is usually stated simply: if the galaxy is old enough and large enough that advanced civilizations should have arisen many times. Where is everybody? The Milky Way is roughly 13 billion years old. It contains several hundred billion stars. Even if only a tiny fraction of those stars host civilizations, and even if those civilizations expand or communicate at even modest rates, the galaxy should be saturated with evidence of intelligence by now. We should see megastructures. We should detect signals. We should find artifacts. We should encounter probes. And yet, as far as we can confirm, we have found none of these things. The possible resolutions of the Fermi paradox are numerous, and none of them are comforting. Perhaps intelligent life is extraordinarily rare, a fluke of Earth-specific history. Perhaps civilizations reliably destroy themselves before achieving interstellar capability. Perhaps they are out there but are deliberately hiding, the so-called zoo hypothesis. Perhaps the galaxy is full of life, but the distances are simply too great for meaningful contact. Perhaps we are looking in the wrong places, at the wrong wavelengths, for the wrong kind of signals. Each resolution implies a different universe, and each carries different implications for humanity's future. Oumuamua landed squarely in the middle of this intellectual landscape. If it were artificial, it would simultaneously confirm the existence of extraterrestrial technology and provide the first piece of physical evidence in the Fermi paradox debate. It would mean that at least one civilization had reached the point of building interstellar devices, and that the galaxy contained enough of these devices for one to wander into our solar system within a few years of our developing the technology to detect it. The implications would be staggering. If it were natural, it would still carry important implications. It would mean that the galaxy is dense with interstellar debris, that the material exchange between stellar systems is far greater than previously assumed, and that the processes of planet formation scatter material into the void on a scale that had not been fully appreciated. Even as a natural object, Oumuamua was revolutionary. It just was not as revolutionary as the alternative. The scientific community, by and large, opted for the natural interpretation, not because they had proven it, but because the alternative was extraordinary in a way that science handles poorly. Extraordinary claims require extraordinary evidence, and Oumuamua's data, while unusual, fell short of the standard required to overturn the baseline assumption that objects in space are natural. This was not unreasonable. It was, in fact, exactly how science is supposed to work. But it left a peculiar taste, because the natural explanations that had been offered were themselves extraordinary in various ways. Hydrogen ice that could not survive interstellar travel. Nitrogen ice that required more material than the galaxy could supply. Trapped hydrogen that had not been experimentally verified. Each natural explanation saved the phenomenon at the cost of invoking conditions that were unprecedented, untested, or statistically implausible. This created what might be called an epistemological stalemate. Neither the natural nor the artificial hypothesis could be confirmed or definitively ruled out. Both required assumptions that went beyond the available evidence. The difference was one of degree. Natural explanations required unusual physics, while the artificial explanation required the existence of an alien civilization. Most scientists reasonably concluded that unusual physics was more likely than alien technology. But the margin between unusual and unprecedented was thinner than many were comfortable admitting. The media coverage amplified the stalemate into something far louder and less nuanced. Headlines reduced complex arguments to binary choices: alien probe or weird rock. Nuance was the first casualty. The careful uncertainties expressed in scientific papers were stripped away in favor of confident declarations. Scientists who said Oumuamua was probably natural were quoted as saying it was definitely natural. Loeb's carefully qualified hypothesis was presented as a confident claim that aliens had visited. The public received a caricature of the debate, not the debate itself. This distortion had consequences. It made scientists even more reluctant to discuss the artificial hypothesis, for fear of being misquoted or sensationalized. It made Loeb's position appear more extreme than it actually was, since the qualifications in his argument were consistently dropped by journalists seeking a cleaner narrative, and it created a feedback loop. The more sensational the coverage, the more the scientific community retreated into defensive conservatism, which in turn made Loeb's criticism of that conservatism appear more justified, which generated more coverage, and so on. There was also a practical dimension to the escalation that had nothing to do with aliens. Oumuamua had exposed a serious gap in humanity's preparedness for interstellar visitors, whether natural or otherwise. When the object was discovered, it was already leaving. The observing window was weeks, not months. No spacecraft could be launched in time to intercept it. The fastest possible mission, even with existing heavy-lift rockets and gravitational assists, would have taken years to catch up with an object moving at 26 kilometers per second outward from the Sun. By the time any spacecraft reached it, Oumuamua would be billions of kilometers away, an impossibly faint target in the outer reaches of the solar system. This was not acceptable, and the scientific community knew it. If the detection of Oumuamua proved that interstellar objects pass through the solar system regularly, then the logical next step was to be ready for the next one. That meant having a spacecraft designed, built, and waiting, ready to launch on short notice toward whatever interstellar visitor appeared next. Several teams began working on mission concepts. The European Space Agency's Comet Interceptor mission, originally designed to study a long-period comet, was recognized as potentially capable of being redirected toward an interstellar object if one were detected in time. Other groups proposed dedicated interstellar object interceptor missions, small, fast spacecraft that could be kept in storage at a Lagrange point and launched within weeks of a detection. The failure to intercept Oumuamua was not a failure of will or imagination. It was a failure of timing. In October of 2017, no spacecraft capable of reaching an object on a hyperbolic trajectory existed anywhere in any state of readiness. The fastest spacecraft ever launched, the Parker Solar Probe, and the New Horizons mission to Pluto, achieved their velocities through careful gravitational assists and years of mission planning. There was no break glass in case of interstellar visitor option. No government had funded one. No agency had built one. The concept had been discussed in theoretical papers but never translated into hardware. The timeline of the missed opportunity was agonizing. Oumuamua was first detected on October 19th. By October 25th, its interstellar origin was confirmed. By early November, the full suite of telescopic observations was underway. By December, the first papers on its anomalous properties were being submitted. The entire window from detection to the loss of the object below observational thresholds was roughly 11 weeks. No spacecraft could have been designed, built, tested, and launched in 11 weeks. Even if one had been sitting on a launch pad, ready to ignite, the orbital mechanics of reaching an object moving at 26 kilometers per second on a trajectory that was not known until October would have required calculations that take days and a flight plan that might take weeks to optimize. The lesson was clear. If humanity wanted to study interstellar visitors up close, the spacecraft had to be ready before the visitor was found. The preparation had to precede the opportunity. This inverted the normal logic of space exploration, where the target is identified first and the mission is designed around it. Interstellar objects demanded a different paradigm. Build the tools first, park them in space, and wait for nature to provide the target. This paradigm shift was one of the most concrete and least controversial outcomes of the Oumuamua encounter. Whatever one believed about the object's nature, the value of being able to intercept and study the next interstellar visitor was undeniable. The scientific return of a close flyby, high-resolution images, compositional measurements, mass estimates, would vastly exceed anything that Earth-based telescopes could provide. It would resolve ambiguities that no amount of theoretical modeling could settle, and it would open a new chapter in planetary science, one in which the material from other stellar systems could be studied directly, rather than inferred from faint points of light. The challenge was immense. Intercepting an interstellar object requires extraordinary velocity. The object is moving fast, on a hyperbolic trajectory, and it does not slow down. A spacecraft must match not only its position, but its speed, which means achieving velocities far beyond what conventional chemical rockets can provide. Solar sails, ion drives, gravity assists, and even nuclear propulsion were discussed as potential solutions. The mission profiles were demanding, requiring launch within days or weeks of detection, a flyby at extremely high relative velocity, and instruments capable of capturing meaningful data in the seconds or minutes of closest approach. But the detection problem was just as challenging. Oumuamua was spotted on its way out. To intercept the next interstellar visitor, it would ideally need to be detected on its way in, before perihelion, while it was still approaching the Sun, and its trajectory could be predicted well in advance. This required survey capabilities far beyond what Pan-STARRS could offer. It required the Vera C. Rubin Observatory. The Vera C. Rubin Observatory, located on the Cerro Pachon Ridge in Chile, was designed to conduct the legacy survey of space and time, known as LSST. When fully operational, Rubin would survey the entire visible sky every few nights using an 8.4-meter primary mirror and the largest digital camera ever built for astronomy, a 3.2 gigapixel detector. Its sensitivity and cadence would represent an order of magnitude improvement over existing surveys. It would detect fainter, more distant and faster-moving objects than any previous telescope. To grasp the scale of this improvement, consider what Pan-STARRS achieved and where it fell short. Pan-STARRS uses a 1.8-meter mirror and covers the sky visible from Hawaii. It detected Oumuamua when the object was already at a distance of roughly 0.2 astronomical units from Earth, about 30 million kilometers, and fading fast. A body twice as distant or half as bright would have been missed entirely. Pan-STARRS was, in effect, watching the cosmos through a keyhole. Rubin will fling the door open. With nearly 20 times the light-gathering area and a camera that can image an area of sky 35 times larger than the full moon in a single exposure, Rubin will routinely detect objects that are 10 to 100 times fainter than what Pan-STARRS can see. It will observe the same patch of sky repeatedly, night after night, building a time-lapse movie of the moving cosmos that captures objects as they brighten, shift position, and evolve. For interstellar object detection, this transforms the game entirely. Models published by researchers at the University of Washington and elsewhere predict that LSST could detect between one and several interstellar objects per year, depending on the true population density. More critically, it should detect them earlier in their trajectories. Oumuamua was caught on its way out. Rubin might catch the next visitor on its way in, perhaps months before perihelion, when it is still brightening and its trajectory can be tracked with precision. This advance warning is the key to everything. With months of lead time, a mission can be planned, instruments can be calibrated, orbits can be computed with enough accuracy to guide a spacecraft to the target. The mission concepts that have been proposed for intercepting interstellar objects are as varied as they are ambitious. At one end of the spectrum, there are proposals for small, fast flyby missions, spacecraft weighing a few hundred kilograms that could be launched on short notice from a parking orbit at the Sun-Earth Lagrange Point 2, about 1.5 million kilometers from Earth. These spacecraft would carry miniaturized cameras, spectrometers, and dust detectors, instruments light enough to be accelerated to the high velocities needed to catch a departing interstellar visitor. The flyby would be brief, lasting minutes or perhaps only seconds at closest approach, but even a brief encounter at close range would yield data of incomparably greater value than anything that can be obtained from Earth. At the other end of the spectrum, there are proposals for more ambitious missions that would not merely fly past an interstellar object, but would match its velocity and travel alongside it, conducting a prolonged study. These rendezvous missions are far more challenging. Matching the velocity of an interstellar object means accelerating to tens of kilometers per second, beyond what is needed to escape the sun's gravity. No existing propulsion system can achieve this efficiently. Solar electric propulsion, which uses ion thrusters powered by solar panels, can produce continuous low thrust over long periods, but is limited by the distance from the sun. Nuclear electric propulsion, which replaces the solar panels with a nuclear reactor, can operate far from the sun but has never been flown in deep space. Solar sail propulsion, which uses radiation pressure from the sun, is theoretically capable of achieving very high velocities but requires enormous sail areas and precise control. Each option is technically feasible in principle, but would require development timescales measured in decades. The most realistic near-term scenario is a flyby mission launched in response to an early detection by Rubin. Such a mission would need to be pre-built and waiting, because the lead time between detection and the optimal launch window might be only weeks or months. This ready-to-go approach has been studied by multiple groups, and the European Space Agency's Comet Interceptor mission represents the first real implementation. Originally designed to study a dynamically new long-period comet, Comet Interceptor has the flexibility to be redirected toward an interstellar object if a suitable target is discovered while the spacecraft is still in its parking orbit. The mission carries 3 modules, a main spacecraft, and 2 smaller probes that will separate before the encounter and observe the target from multiple angles simultaneously. Comet Interceptor is not specifically designed for interstellar objects. Its velocity capability is limited compared to what an ideal interstellar interceptor would need, but it represents a proof of concept, a spacecraft that waits for a target of opportunity rather than being launched toward a known destination. This philosophy of responsive opportunistic missions is new in planetary science, where the traditional approach is to identify a target, design a mission around it, build the spacecraft over a decade, and launch it toward a destination chosen years in advance. Interstellar objects demand a fundamentally different approach. They appear without warning, offer brief observing windows, and then vanish. The spacecraft must be ready before the target is found. This reversal of the usual sequence, building the tool before knowing what it will study, is one of the conceptual innovations that Oumuamua forced upon the field. For interstellar object detection, Rubin was transformative. Models predicted that LSST could detect one or more interstellar objects per year, possibly many more, and crucially, detect them earlier in their trajectories, potentially while still inbound. This would provide the advance warning needed for an intercept mission. It would also provide a statistical sample. With Oumuamua and Borisov, the sample size was 2. Two objects were not enough to draw general conclusions about the population of interstellar visitors. With Rubin, the sample could grow to dozens or hundreds over the survey's 10-year baseline, allowing researchers to determine whether Oumuamua was an anomaly or representative of a common class of objects. The prospect of a larger sample was, in many ways, more important than any individual detection. If future interstellar objects showed the same anomalies as Oumuamua, the extreme shape, the anomalous acceleration, the lack of outgassing, it would suggest that these features were common, which would in turn constrain or eliminate many of the proposed explanations. If, on the other hand, future objects all resembled Borisov, clearly cometary and unremarkable, Oumuamua would stand alone as an outlier, its mystery deepened, but perhaps explained as a statistical fluke, the one weird object in a sea of normal ones. The scientific debate over Oumuamua also revealed something important about the way modern research is conducted and communicated. In the traditional model, scientific controversies play out slowly through journal publications, conference presentations, and peer review. Results are published, critiqued, replicated, and revised over timescales of years or decades. The Oumuamua debate did not follow this model. It played out simultaneously in journals and on social media, in peer-reviewed papers, and on popular podcasts, in academic seminars, and in newspaper columns. The traditional gatekeeping mechanisms of science, peer review, editorial oversight, the slow consensus building of conference discussions, were overwhelmed by the speed and reach of modern communication. This was not entirely negative. The rapid dissemination of results meant that errors were caught quickly, alternative hypotheses were proposed within weeks rather than months, and the global scientific community could participate in the debate in near real time. The trapped hydrogen hypothesis, for example, benefited from the accumulated work of multiple research groups who had been spurred by the public interest in the problem. Without the attention that Loeb's provocative claims had generated, it is possible that fewer researchers would have devoted time to the puzzle, and the most promising natural explanation might have been slower to emerge. But the speed of the debate also had costs. Nuance was lost. The differences between "this hypothesis is consistent with the data" and "this hypothesis is correct" were eroded in popular reporting. Scientists found themselves pressured to take definitive positions when the evidence warranted only tentative ones. And the adversarial dynamic between Loeb and his critics sometimes resembled a political campaign more than a scientific discussion, with each side appealing to public opinion rather than engaging solely with the data. There was a deeper structural issue at work as well. The Oumuamua debate exposed the challenge that modern science faces when dealing with phenomena that sit at the intersection of multiple disciplines. The object's trajectory was a problem for celestial mechanics. Its composition was a problem for planetary science. Its acceleration was a problem for cometary physics. Its possible artificial origin was a problem for SETI. And the question of how to handle inconclusive evidence about extraordinary claims was a problem for the philosophy of science. No single discipline owned the question, and the experts in each discipline brought different standards of evidence, different prior assumptions, and different tolerance for speculation. A dynamicist might be satisfied with a mathematical model that fits the trajectory. A planetary scientist might demand a physical mechanism for the acceleration that was consistent with known materials. A SETI researcher might argue that the artificial hypothesis should be evaluated on equal footing, and a philosopher of science might point out that all of these positions were shaped by unstated assumptions about what counts as extraordinary. This disciplinary fragmentation made the debate harder to resolve, because there was no single community with the authority to declare a consensus. In a debate confined to, say, stellar astrophysics, there is a community of experts who share a common training, common standards, and common methods. They can eventually converge on a consensus through the normal mechanisms of scientific discourse. The Oumuamua debate spanned too many communities for this to work. Each group had its own criteria for what would constitute a satisfying explanation, and those criteria did not always align. The result was a kind of productive gridlock. No consensus emerged, but the attempts to build one generated a wealth of new science. Models of interstellar object formation, evolution, and detection were developed. Laboratory studies of ice physics under interstellar conditions were initiated. The theoretical connection between planetary system architecture and the properties of ejected debris was explored in detail. Mission design studies were funded, and the practical question of how to detect and characterize future interstellar visitors was addressed with a seriousness that would have been unthinkable before Oumuamua. The role of individual personality in the debate also deserves reflection. Avi Loeb is not the first scientist to propose a bold hypothesis. He is not the first to write a popular book arguing for an unconventional position. What made his intervention distinctive was the combination of his institutional authority, his willingness to engage with the media directly rather than through the mediated channels of academic publishing, and his explicit framing of the debate as a test of the scientific community's open-mindedness. By positioning himself as the lone voice of reason against a hidebound establishment, Loeb forced a conversation that might not have happened otherwise. But he also polarized it in ways that made dispassionate evaluation more difficult. His critics, for their part, were not uniformly fair. Some dismissed the artificial hypothesis without engaging seriously with the physics behind it. Others attacked Loeb's motivations rather than his arguments. And the general atmosphere of the debate, in which suggesting that an object might be artificial was treated in some quarters as a professional disgrace rather than a scientific hypothesis, said something uncomfortable about the boundaries of acceptable inquiry in modern astronomy. The question of whether those boundaries are drawn in the right place is not one that Oumuamua resolved, but it is one that Oumuamua made impossible to ignore. There was also a generational dimension to the debate that was rarely discussed explicitly, but was evident in the patterns of response. Younger researchers, particularly graduate students and early career scientists, were often more willing to entertain the artificial hypothesis, or at least to treat it as a legitimate topic of discussion. They had grown up in a culture where exoplanets were routine discoveries, where SETI had been partially rehabilitated, and where the search for biosignatures in exoplanetary atmospheres was an established research program. For them, the idea that technology might exist beyond Earth was not inherently absurd. It was simply another hypothesis to be evaluated against data. Senior researchers, by contrast, had spent their careers building reputations within disciplinary frameworks that did not include the search for alien technology. They had institutional commitments, professional networks, and funding relationships that were built on conventional research topics. For them, the artificial hypothesis was not merely unlikely, it was professionally dangerous. Endorsing it, or even engaging with it too enthusiastically, carried career risks that younger researchers might not fully appreciate. This asymmetry of risk shaped the debate in ways that had nothing to do with the strength of the evidence and everything to do with the sociology of scientific careers. The escalation of the Oumuamua debate had thus produced something valuable alongside the noise and controversy. It had catalyzed a genuine scientific mobilization. New instruments were being planned, new mission concepts were being developed, new theoretical frameworks were being constructed. The community was preparing for the first time in human history, to study interstellar objects systematically rather than scrambling to observe them in retrospect. Whether Oumuamua was a chunk of exotic ice or a fragment of alien technology, it had forced humanity to confront the fact that the solar system is not isolated. Things come in from outside. They always have. And now, finally, we were beginning to prepare to study them properly. But the deeper question remained unanswered, and perhaps unanswerable in the near term. How should science handle a mystery that is permanently data-limited? When the object of inquiry has vanished and cannot be recalled, when the data on hand is consistent with multiple contradictory explanations, when the cultural stakes of the answer are enormous, how does a rational community proceed? This was the question that Oumuamua had really posed. Not what was it, but how do we decide what it was when we can never check? That question would require a different kind of thinking, not the physics of interstellar objects, but the philosophy of evidence, the sociology of scientific communities, and the hard, honest reckoning with the limits of human knowledge. The complications had escalated into something larger than a debate about a single object. They had become a debate about the nature of certainty itself. Here is where we step back from the competing hypotheses and ask a different question. Not what was Oumuamua, but what did Oumuamua teach us? Because the most important lesson of this story may not be about the object at all. It may be about the species that found it. Consider the situation from the perspective of a rational observer trying to weigh the evidence. On one side, there are natural explanations. Each one accounts for some of the anomalies, but none accounts for all of them without invoking conditions that are themselves unusual. Hydrogen ice explains the invisible outgassing but cannot survive interstellar travel. Nitrogen ice explains the shape and the accelerations, but requires more material than the galaxy can provide. Trapped hydrogen from cosmic ray radiolysis is the most promising, but it has not been experimentally confirmed at the required scale. On the other side, there is the artificial hypothesis. It accounts for all the anomalies simultaneously. A thin, lightweight object propelled by radiation pressure needs no outgassing, explains the extreme shape, and naturally produces the observed acceleration. But it requires the existence of extraterrestrial technology, a claim that has never been confirmed, and that carries an evidential burden so heavy that no single observation of a distant, fading point of light could plausibly satisfy it. A Bayesian approach to this problem would assign prior probabilities to each hypothesis based on what we already know about the universe, then update those priors based on the observed data. The prior probability of any given interstellar object being artificial technology is, by most reasonable estimates, extremely low. The universe has been producing natural objects for nearly 14 billion years through well-understood physical processes. The number of natural interstellar objects in the galaxy is estimated to be in the trillions of trillions. Against this vast background, even if technological civilizations exist, the fraction of interstellar objects that are artificial would be vanishingly small. The prior is minuscule. The data from Oumuamua does shift the probability. An object with an unprecedented shape, anomalous acceleration, and no detectable outgassing is more consistent with the artificial hypothesis than a randomly selected natural object would be. The likelihood ratio favors the artificial explanation to some degree, but in Bayesian terms, even a moderately favorable likelihood ratio applied to an extremely small prior still produces a small posterior probability. The math does not rescue the alien hypothesis from its low starting point. It moves the needle, but not nearly enough. This is frustrating for those who find the artificial hypothesis compelling, but it is how probabilistic reasoning works. The extraordinary nature of the claim establishes a high evidential bar, and the data, while unusual, does not clear it. This does not mean the artificial hypothesis is wrong. It means it cannot be confirmed by this data alone. The two statements are very different, and confusing them is one of the most common errors in the public discussion of Oumuamua. But there is a subtlety here that deserves careful attention. The Bayesian framework depends critically on the prior, and the prior depends on assumptions that are themselves uncertain. How common are technological civilizations? How often do they produce interstellar debris? How long does that debris survive? These are precisely the unknowns in the Drake equation, and they span orders of magnitude of uncertainty. If civilizations are common and long-lived, the prior for artificial objects is much higher than if civilizations are rare and brief. The choice of prior is not a neutral, objective act. It is itself an expression of belief about the universe, shaped by the very question we are trying to answer. This circularity is not a flaw in Bayesian reasoning, it is a feature. It makes explicit what is otherwise hidden. That our conclusions about Oumuamua depend not only on the data, but on our background assumptions about the prevalence of intelligence in the universe, assumptions that are themselves deeply uncertain. Anyone who claims to know the answer with high confidence, whether natural or artificial, is smuggling in assumptions that the data cannot support. The honest answer, the answer that most closely respects the limits of available evidence, is that we do not know what Oumuamua was. We have a set of observations that are genuinely anomalous. We have a menu of hypotheses, each with strengths and weaknesses. We have no way to gather additional data on this specific object, and we have a powerful set of tools, the Rubin Observatory, proposed interceptor missions, the Galileo project, that may one day provide the context needed to understand what Oumuamua represented. Until then, the intellectually courageous position is not certainty in either direction. It is the patient, disciplined acknowledgement of uncertainty. This is harder than it sounds. Humans are not wired for sustained uncertainty. The brain craves resolution. It wants to close the file, to assign a label, to move on. Ambiguity is uncomfortable, and the specific kind of ambiguity presented by Oumuamua, the possibility, however remote, that we encountered alien technology and were unable to confirm it, is uniquely disquieting. The natural response is to resolve the tension by choosing a side. Either it was definitely natural, in which case the disquiet is unwarranted, or it was definitely artificial, in which case the disquiet becomes excitement. Both resolutions offer emotional comfort. Both are epistemically premature. The scientific community, to its credit, has mostly resisted the temptation to declare the mystery solved. Papers continue to be published. New models continue to be proposed. The trapped hydrogen hypothesis is being investigated experimentally. Theoretical work on the expected properties of interstellar objects continues to advance. The question remains genuinely open, not because scientists cannot make up their minds, but because the evidence genuinely does not support a definitive conclusion. It is worth examining what a definitive conclusion would actually look like, because the standards of proof differ radically depending on which hypothesis is being tested. For the natural explanations, confirmation would require one of two things: either the experimental verification of the trapped hydrogen mechanism at the quantities needed to produce the observed acceleration, or the detection of another interstellar object with similar anomalies that also has a measurable spectral signature revealing its composition. The first path is being pursued in laboratories. The second depends on the next interstellar visitor and the instruments available to study it. Both paths are scientifically tractable, meaning they can, in principle, be pursued with existing or planned technology. They require patience, funding, and the good fortune of detecting a suitable target, but they are not impossible. For the artificial hypothesis, the standard of proof is far higher and far harder to meet. No amount of modelling or laboratory work could confirm that Oumuamua was a light sail. That confirmation would require either a close-up observation of the object itself, which is permanently impossible, or the detection of unambiguous technological signatures, deliberate electromagnetic emissions, manufactured materials, non-random structural features on a future interstellar visitor. The artificial hypothesis is not just difficult to confirm, it is difficult to even specify what confirmation would look like. What distinguishes a thin natural disk from a thin artificial membrane when observed as a faint point of light at millions of kilometers? The answer, in terms of photometric and spectroscopic data, may be nothing. They could look identical. This asymmetry in testability is a crucial and often overlooked aspect of the debate. The natural hypotheses are, in principle, falsifiable through specific observations or experiments. The artificial hypothesis is not falsifiable with the data we have, or are likely to obtain in the near term. This does not make the artificial hypothesis wrong. unfalsifiable hypotheses can be true, but it does place the hypothesis outside the normal framework of scientific testing, which relies fundamentally on the ability to distinguish between competing explanations through new observations. The artificial hypothesis floats in a kind of evidential limbo, neither confirmed nor refuted, immune to the tools that science normally uses to resolve disputes. Some scientists have argued that this very unfalsifiability should disqualify the artificial hypothesis from serious discussion. If a hypothesis cannot be tested, it is not a scientific hypothesis, regardless of how mathematically elegant or emotionally compelling it may be. Others have countered that the unfalsifiability is contingent, not inherent. The hypothesis is untestable now, with current data and technology, but future detections of interstellar objects, future missions, future instruments could provide data that would make the hypothesis testable. Excluding it permanently on the grounds of current untestability would be premature. This debate about testability echoes much older arguments in the philosophy of science. Karl Popper famously argued that the demarcation between science and non-science was falsifiability. A hypothesis is scientific if and only if it can, in principle, be refuted by observation. Thomas Kuhn countered that real science does not work that neatly, that scientists routinely work within paradigms that contain unfalsifiable assumptions, and that scientific revolutions happen not through falsification but through the accumulation of anomalies that eventually force a paradigm shift. Oumuamua can be read through either lens. For a Popperian, the artificial hypothesis fails the demarcation criterion and should be set aside. For a Kuhnian, Oumuamua is an anomaly that does not fit the existing paradigm of cometry and asteroidal science, and the resistance to the artificial hypothesis is itself a feature of normal science, protecting an established paradigm against a disturbing interloper. Neither reading is entirely satisfying. The Popperian view risks excluding a hypothesis that might be true simply because the tools to test it do not yet exist. The Kuhnian view risks treating every anomaly as a potential revolution, which would make science incoherent. The resolution, if there is one, probably lies in a pragmatic middle ground. Take the artificial hypothesis seriously enough to design observations that could test it, but do not treat it as confirmed simply because it is consistent with limited data. This is, in practice, what the best scientists in the field are doing. They are designing the next generation of observations with the artificial hypothesis in mind, not because they believe it, but because they recognize that excluding it from consideration would mean missing the chance to test it if the opportunity ever arises. There is one more dimension to the turn that deserves attention: the role of time. In most scientific debates, time is an ally. More data arrives, instruments improve, techniques are refined. The fog of initial uncertainty gradually lifts, and the truth, or some closer approximation of it, emerges. But in the case of Oumuamua, time is working against resolution. The object is getting farther away. The data is not going to improve. The memories of the observations will persist in journals and databases, but the object itself is receding at a pace that will place it beyond any conceivable human reach within a few decades, even with spacecraft that do not yet exist. This creates a peculiar situation in the history of science. Most unsolved scientific problems are unsolved because we do not yet have the tools or the insights needed to solve them. The tools will eventually be built. The insights will eventually come. The problem of Oumuamua is different. It is unsolved because the primary evidence has left the building. The tools needed to solve it may exist, but they needed to be deployed in 2017, and they were not available then. The problem is not a gap in knowledge that will be filled by progress. It is a gap in knowledge that was created by the irrecoverable passage of a unique event. This kind of problem, the unrepeatable observation, the fleeting event that leaves ambiguous traces, is familiar in other areas of inquiry. It is the daily reality of archaeology, paleontology, and forensic science, disciplines that routinely deal with fragmentary evidence of past events that cannot be reobserved. Those disciplines have developed sophisticated methods for extracting maximum information from minimal data, and some of those methods have been applied to Oumuamua. But the analogy is imperfect because archaeology and paleontology deal with populations of events. There are many fossils, many dig sites, many crime scenes. Each individual case may be ambiguous, but the aggregate provides constraints that resolve many questions. With Oumuamua, the sample size is 1. There is no aggregate. There is no statistical baseline for anomalous interstellar objects against which Oumuamua can be compared. It stands alone, unprecedented and unrepeated, a single data point in a parameter space that has not been mapped. And yet, the turn in this story is not about the resolution of the mystery. It is about the transformation that the mystery produced. Because regardless of what Oumuamua was, it changed things. It changed what we know about the galaxy, what we look for in the sky, and how we think about our place in the cosmos. Those changes are real and permanent, and they do not depend on the answer to the question of origin. Start with what we learned about the interstellar medium. Before Oumuamua, the existence of interstellar objects was theoretical. Models of planet formation predicted that the process of building planets from a protoplanetary disk is inherently wasteful. Not all material gets incorporated into planets, moons, or asteroids. Some is gravitationally scattered by the giant planets during their formation and migration, flung out of the system entirely on hyperbolic trajectories. This ejected material, chunks of rock, ice, and mixed compositions, becomes interstellar debris, drifting through the galaxy on trajectories determined by the gravitational dynamics of their home systems and the general galactic potential. The prediction was straightforward. The confirmation was not. Detecting a small, dark, fast-moving object against the background of space is extraordinarily difficult. Before pan-stars and similar wide-field surveys, the probability of catching one was effectively zero. Oumuamua's detection was the first direct confirmation that the galaxy's interstellar space is indeed populated with debris from other star systems. That single data point, combined with the probability of detection, allowed astronomers to estimate the density of interstellar objects for the first time. The result was staggering. The implied population density was far higher than most pre-detection models had predicted, suggesting that every star in the galaxy contributes substantially to the interstellar debris field. The galaxy is not empty between the stars. It is filled with the detritus of planet formation, a vast, invisible sea of wandering objects, each carrying information about the chemical composition and dynamical history of its home system. The implications for planet formation theory were significant. The amount of material ejected by a planetary system during its formation depends sensitively on the architecture of that system, the number and masses of its giant planets, the timing of their migration, and the structure of the original protoplanetary disk. By measuring the density of interstellar objects near the Sun, astronomers could, for the first time, place observational constraints on the average ejection efficiency of planetary systems across the galaxy. The preliminary results suggested that ejection is extremely efficient, that most planetary systems lose a substantial fraction of their initial solid material to interstellar space. This has consequences for models of planet formation, because the material that is ejected is material that is not available to build planets. A galaxy with high ejection efficiency is a galaxy where planets form in the presence of significant mass loss, and that mass loss shapes the final planetary architectures in ways that theorists are only beginning to explore. There was also a chemical dimension to the discovery. The composition of an interstellar object is a frozen record of the chemical environment in which it formed. If its home system was rich in water ice, the object carries that signature. If it formed in a region with unusual isotopic ratios, those ratios are preserved. Each interstellar visitor is, in effect, a message in a bottle, carrying information about the chemistry of a distant stellar nursery across the galaxy. Reading that message requires getting close enough to take a spectrum, which we could not do with Oumuamua, but which future missions may accomplish with the next detection. This has profound implications for our understanding of how material moves through the galaxy. The concept of panspermia, the hypothesis that life or its precursors can be transported between star systems by interstellar objects, had always been speculative, but the high density of interstellar objects implied by Oumuamua made the transport mechanism far more plausible. If trillions of objects cross between stellar neighborhoods over galactic timescales, and if some of those objects carry organic molecules or even dormant microorganisms, the seeds of life could be far more mobile than previously imagined. This does not prove that panspermia occurs, but it moves the concept from science fiction to a legitimate area of astrobiological inquiry. The detection also transformed the practice of solar system astronomy. Before 2017, the survey programs that scan the sky for near-Earth objects, potential impact hazards, comets, and distant Kuiper Belt objects were not designed to detect interstellar visitors. Their software was optimized for objects on bound elliptical orbits, objects on hyperbolic trajectories, which appear as faint streaks moving at unusual speeds and angles, could be missed or flagged as artifacts. After Oumuamua, survey pipelines were updated to include algorithms specifically designed to identify objects on unbound orbits. The detection of Borisov in 2019 validated these improvements and demonstrated that the surveys could now reliably identify interstellar visitors. This was a quiet revolution. It received none of the headlines that the alien hypothesis generated, but it was arguably more important because it converted a once-in-history fluke into a repeatable scientific program. The next interstellar object would not catch us completely off guard. It would be detected earlier, observed more thoroughly, and studied with instruments specifically designed for the purpose. Oumuamua was found by accident. Future interstellar objects would be found by design. The theoretical response was equally transformative. Before Oumuamua, the study of interstellar objects was a niche topic, pursued by a small number of dynamicists and planetary scientists. After Oumuamua, it became a major area of research attracting talent from across astrophysics. Dozens of papers were published on the formation, evolution, and detectability of interstellar objects. New models explored how objects are ejected from their home systems, how they interact with the interstellar radiation field, how their surfaces evolve during their long journeys, and what signatures they should display when they enter a new star system. The theoretical framework for understanding these visitors, which barely existed before 2017, was substantially built out within 5 years. One particularly important theoretical development concerned the diversity of interstellar objects. The sample size was only 2, but the two members of that sample, Oumuamua and Borisov, were radically different from each other. Borisov was a recognizable comet. Oumuamua was something else entirely. This suggested that the interstellar population was not homogeneous. It likely included a wide range of compositions and histories, from icy comet fragments to rocky remnants to objects that had been altered in ways that their home system's inhabitants, if any, would not recognize. The diversity of the interstellar debris field is a direct reflection of the diversity of planetary systems in the galaxy, and studying it is, in effect, studying the chemical and dynamical history of the Milky Way through its discarded material. There was also a philosophical transformation that deserves acknowledgement. Oumuamua forced the astronomical community to confront, seriously and publicly, the question of how to handle potential evidence of extraterrestrial technology. This had always been a hypothetical exercise, a thought experiment discussed in seminars and science fiction. Oumuamua made it real, not because the object was proven to be artificial, but because the data was ambiguous enough that the possibility could not be dismissed out of hand. For the first time, the scientific community had to develop protocols for dealing with anomalous objects that might, just might, be artificial. What kind of evidence would be sufficient? Who would make the determination? How would the information be communicated to the public? These questions had been asked before in the context of SETI radio signals, but Oumuamua added a new dimension: the physical artifact, the object you can see and track, but cannot reach. This practical reckoning with the possibility of discovery, even an inconclusive one, was itself a milestone. It moved the discussion of extraterrestrial technology from the realm of pure speculation into the realm of observational science. It did not prove anything about alien civilizations, but it proved that the question could be engaged scientifically, with data, models, and Bayesian reasoning, rather than dismissed reflexively or embraced credulously. That shift in approach, that willingness to treat the question as a legitimate scientific problem rather than a cultural taboo or a tabloid fantasy, may be Oumuamua's most lasting contribution. The turn, then, is this. The story of Oumuamua is not ultimately a story about an alien light sail or an exotic ice comet. It is a story about the scientific method under pressure. It is about what happens when nature presents an observation that resists easy classification, when the data runs out before the question is answered, and when the cultural stakes of the answer distort the process of inquiry. It is about the tension between rigor and imagination, between caution and courage, between the demand for certainty and the reality of ambiguity. And from that tension, something genuinely new emerged, a new field of study, new instruments, new mission concepts, new theoretical frameworks, a new willingness to engage with previously taboo questions, and perhaps most importantly, a new humility about the limits of what we know. For Oumuamua, it was easy to assume that the categories of solar system science, asteroid, comet, planet, moon, covered the full range of possibilities. After Oumuamua, it was clear that the universe might contain objects that fit none of our existing categories, objects whose nature can only be understood by abandoning the assumption that we have already catalogued every type of thing that exists. The turn is not a resolution, it is a reorientation. It points forward, toward the next interstellar visitor, the next dataset, the next opportunity to test the hypotheses that Oumuamua generated, but could not resolve. It acknowledges that some mysteries are not solved by thinking harder about existing data, but only by gathering new data entirely. And it accepts, with difficulty but with honesty, that the question "what was Oumuamua?" may remain open for years, decades, or perhaps forever. But the forward-looking posture is not passive. It is actively preparing. The instruments are being built, the missions are being designed, the algorithms are being written. And the next time an interstellar object enters the solar system, humanity will be ready in a way it was not in October of 2017. That readiness is Oumuamua's most concrete legacy, more tangible than any hypothesis, more durable than any headline. The frustration of not knowing is real. The discomfort of ambiguity is real, but so is the progress that ambiguity has produced. Oumuamua did not give us answers. It gave us better questions. And in science, better questions are often worth more than premature answers. There is a moment, near the end of every profound discovery, when the mind shifts from asking, "What is it?" to asking, "What does it mean for us?" This shift is not a departure from science. It is its natural continuation. Facts exist within frameworks of meaning, and the meaning of Oumuamua extends far beyond its trajectory, its shape, or the unresolved question of its origin. Begin with the most fundamental implication. Oumuamua demonstrated that our solar system is not a closed system. Objects from other parts of the galaxy enter our neighborhood, pass through, and leave. They have been doing this for billions of years. The sun's gravitational domain is not a fortress with walls. It is a clearing in a vast forest, and things wander through it. Some are large enough to detect. Most are not. But the traffic is constant, and it has been constant since the solar system formed. This realization reshapes our understanding of Earth's history. If interstellar material regularly passes through the inner solar system, some of it must have occasionally struck the Earth. Over 4.5 billion years, the number of interstellar impacts, while small compared to the total bombardment from within the solar system, is not zero. Some of those objects may have carried organic molecules. Some may have carried water ice with unusual isotopic signatures. Some may have deposited material on Earth's surface that influenced the chemistry of the early ocean or atmosphere in ways that are impossible to distinguish from indigenous material billions of years later. The hard boundary between our stuff and their stuff, between material that formed here and material that formed around another star, is not as sharp as we once assumed. This has implications for the origin of life. The question of whether life arose independently on Earth or was seeded by material from elsewhere is one of the oldest and most stubborn questions in biology. Oumuamua did not answer it, but it made the seeding mechanism more plausible by demonstrating that interstellar transport is real, frequent, and involves objects that pass through the habitable zone of the inner solar system. If life or its molecular precursors can survive the radiation environment of interstellar space, and if they can survive atmospheric entry and impact, then the delivery system exists and operates at a rate sufficient to make panspermia a genuine possibility rather than a speculative fantasy. Beyond biology, Oumuamua carries implications for the future of human civilization. We are, at this moment in history, a species that has just barely developed the technology to detect interstellar visitors. Pan-STARRS, Ruben, the various survey programs that scan the sky, are the first generation of instruments capable of spotting these objects. We are, in astronomical terms, newborns. We have opened our eyes for the first time and seen something unexpected in the sky, and we do not yet have the tools to understand it fully. But we are building those tools, and the next time something comes through, we will see it sooner, study it more thoroughly, and perhaps, if we are prepared, send a spacecraft to meet it. This is a pivotal moment. The transition from passively observing interstellar objects to actively studying them and eventually intercepting them represents a qualitative change in humanity's relationship with the galaxy. For the entirety of human history, the stars have been points of light, impossibly distant, unreachable. The planets of our solar system have, over the past few decades, become places we can visit with robotic explorers. But the material between the stars, the objects that carry information about other planetary systems, has been beyond our reach. Oumuamua was the first tangible piece of another stellar system to pass through our neighborhood and be recognized as such. The next one might be caught. Imagine for a moment what that would mean. A spacecraft launched to intercept an interstellar object could, even in a brief flyby, gather data of extraordinary value. Close-up images would reveal the surface structure and morphology. Spectrometers could determine the chemical composition. A dust collector might capture material that formed around another star, material with a different isotopic fingerprint than anything in our solar system. For the first time, we would hold a piece of another world, not a world we chose to visit, but a world that came to us. The scientific return would be incalculable, and if the object were anomalous, if it displayed the same kind of unexplained characteristics as Oumuamua, a close encounter would provide the data needed to resolve the ambiguity. Not through argument, not through modelling, not through the endless back and forth of competing hypotheses, but through direct observation. The camera does not argue, it records. And a high-resolution image of an interstellar object's surface would settle more questions in a single frame than 1,000 theoretical papers. There is also a dimension of Oumuamua's legacy that is less romantic and more urgent. Planetary defense. The discovery exposed a vulnerability that had not been fully appreciated. Our planetary defense infrastructure, the network of telescopes and tracking systems designed to identify asteroids and comets that might collide with Earth, was optimized for objects originating within the solar system. These objects move on predictable elliptical orbits. They can be tracked over years. Their trajectories can be computed with high precision. If one is found to be on a collision course, there is typically time, years or decades, to mount a deflection effort. Interstellar objects are different. They arrive on hyperbolic trajectories from arbitrary directions at velocities that can exceed anything produced within the solar system. They provide far less warning time. An interstellar object on a direct collision course with Earth might be detected only weeks or months before impact, and at velocities of 20 to 60 kilometers per second, the kinetic energy of even a modestly sized impactor would be devastating. The deflection techniques being developed for solar system asteroids, kinetic impactors like NASA's DART mission, gravity tractors, laser ablation, all require years of lead time that an interstellar impactor might not provide. The probability of an interstellar object striking Earth is extremely low. The cross-section of the Earth is tiny compared to the volume of space through which these objects travel, but the probability is not zero, and the consequences of such an impact would be severe and essentially unpreventable with current technology. Oumuamua brought this scenario from the purely theoretical to the observationally grounded. We now know that interstellar objects exist, that they pass through the inner solar system regularly, and that some of them are large enough to cause significant damage. incorporating interstellar impactors into planetary defense planning is no longer an academic exercise. It is a practical necessity. But perhaps the most important reflection prompted by Oumuamua is not about any specific scientific question. It is about the human relationship with the unknown. For most of human history, the universe beyond the solar system was an abstraction. Stars were points of light. Other planetary systems were hypothetical. The space between stars was assumed to be empty. Within a single generation, that picture has been completely overturned. We now know that other planetary systems are ubiquitous. We know that some of them harbour planets in habitable zones. We know that material is exchanged between these systems, and we know that some of that material is strange enough to defy easy explanation. The pace of this transformation is breathtaking. The first exoplanet orbiting a Sun-like star was confirmed in 1995, barely 3 decades ago. The first interstellar object was detected in 2017. The first interstellar comet was found in 2019. Within a span of 25 years, humanity went from knowing of 0 planets outside the solar system to knowing of thousands, and from theorizing about interstellar debris to detecting it. The rate of discovery is accelerating, driven by instruments of increasing power and surveys of increasing scope. In this context, Oumuamua is not an endpoint, it is a beginning, the first chapter of a story that will unfold over the coming decades as new telescopes come online, as interstellar objects are detected and studied in growing numbers, and as the population of wanderers between the stars is characterized for the first time. Some of those objects will be mundane, some will be surprising, and some, perhaps, will be genuinely anomalous in ways that force us to expand our understanding of what the universe contains. There is something deeply moving about this moment in human history. For hundreds of thousands of years, our species looked up at the night sky and saw only points of light, beautiful but inaccessible, fixed and eternal. Then, over the past 4 centuries, we developed the tools to understand those points of light, to measure their distances, to determine their compositions, to recognize them as suns like our own. In the past 3 decades, we discovered that many of those suns harbour planets. And now, in the past decade, we have learned that the space between those suns is not empty but populated with wanderers, objects that carry the chemical memory of other worlds and that occasionally pass through our neighbourhood close enough to detect. Each of these revelations has expanded the boundary of what we consider home. At first, home was Earth, then it was the solar system, then it was the local stellar neighbourhood. Now, with the detection of interstellar objects, home extends to the galactic commons, the shared space through which material from many stellar systems mingles and drifts. We are not isolated. We never were. The material that built our planet, the atoms in our bodies, the water in our oceans, all of it was forged in earlier generations of stars and dispersed through the galaxy by the same processes that produce interstellar debris. In a very real sense, Oumuamua was not a stranger visiting from afar. It was a relative, a distant cousin formed from the same galactic inheritance that built the Earth. The material was different, the history was different, but the origin, the same galaxy, the same physical laws, the same processes of stellar birth and planetary formation, was shared. Let that sink in. Every interstellar object that passes through the solar system carries atoms that were cooked in the nuclear furnaces of stars that died before our sun was born. Those atoms drifted through molecular clouds, accreted into planetesimals around other stars, were ejected by the gravitational dynamics of other planetary systems, and then wandered through the galaxy for eons before arriving here. The journey of a single atom from the core of a dying star to the surface of an interstellar visitor to our detection is a story that spans billions of years and hundreds of light years. We are witnesses to the final chapter of that journey, the brief, bright moment when the object crosses our path and catches the light of our particular star. This is not science fiction. This is the ordinary operation of the galaxy. It has been happening since the first planetary systems formed, billions of years before the Earth existed. It will continue long after the sun burns out and the solar system disperses into the same interstellar medium from which it coalesced. The traffic is ancient, and it is endless. Oumuamua was simply the first piece of that traffic that we were able to see. The proper response to this situation is neither dismissal nor hysteria. It is preparation. Preparation of instruments, preparation of missions, preparation of theoretical frameworks, and preparation of mind. The universe is under no obligation to present us only with phenomena that fit neatly into existing categories. It will, with serene indifference, continue to produce surprises. Our job is to be ready for them, to observe with clear eyes, to reason with disciplined minds, and to accept with equanimity the possibility that some things will remain unknown for longer than we would like. Oumuamua tested that equanimity. It tested the scientific community's ability to handle ambiguity, to resist the pressure for premature certainty, and to continue working productively on a problem that might never be solved. In many ways, the community passed that test. The research continued. The instruments were funded. The theories were developed. The debate, while sometimes acrimonious, remained within the bounds of scientific discourse. No consensus was forced. No hypothesis was declared by fiat. The question remained open because the evidence demanded that it remain open, and the community respected that demand. That respect for evidence, even when it leads to uncomfortable uncertainty, is the essence of the scientific enterprise. It is what distinguishes science from ideology, from religion, from mere opinion. Science does not promise answers. It promises honest inquiry. An honest inquiry sometimes leads to a long, sustained encounter with not knowing. Oumuamua was one of those encounters. It may not be the last. In the end, here is what we know for certain. On October 19, 2017, a small, dark, reddish object was detected by the Pan-STARRS 1 telescope on the summit of Haleakala in Hawaii. It was moving too fast to be bound to the sun. It had come from interstellar space, from a direction near the constellation Lyra. It was the first interstellar object ever identified by human observers. It was given the Hawaiian name Oumuamua, meaning a scout or messenger from the distant past, arriving first. Its shape was extreme, with a brightness variation of roughly 10:1 implying an axial ratio of at least 6:1. Its surface was dark, absorbing more than 90% of incident light, coated in an irradiation mantle, built up over millions or billions of years of exposure to galactic cosmic rays. Every search for cometary activity, water vapor, carbon dioxide, carbon monoxide, dust, returned nothing. The object appeared completely inert, and yet it was accelerating. A tiny but unmistakable non-gravitational force was pushing it away from the sun, a force consistent in magnitude with cometary outgassing, but contradicted by the total absence of any detected gas or dust. The only conventional mechanism that could explain the acceleration was the one mechanism that the observations ruled out. Multiple hypotheses were proposed. Water ice outgassing, invisible to instruments, was the first suggestion. It was consistent with the acceleration but struggled to explain the absence of dust, spin changes, and the extraordinary quantities of mass loss required. Hydrogen ice was proposed and found wanting because it could not survive the journey through interstellar space. Nitrogen ice was proposed and found to require more raw material than the galaxy could plausibly supply. Trapped hydrogen from cosmic ray radiolysis of water ice was proposed and remains the most promising natural explanation, though it has not yet been experimentally confirmed at the required scales. And then there was the other hypothesis, the one that made headlines, provoked outrage, spawned a best-selling book, and divided a scientific community. Avi Loeb proposed that Oumuamua was a light sail, a thin, flat object propelled by solar radiation pressure, either a functional probe or a piece of discarded technology from an extraterrestrial civilization. The physics was correct. The cultural reaction was fierce. The hypothesis could not be confirmed, it could not be ruled out, and the object that might have settled the matter was already beyond the reach of every telescope on Earth or in space. That is where the story stands today. Oumuamua is somewhere beyond the orbit of Neptune, still moving outward at roughly 26 kilometers per second, growing more distant by about 2.3 million kilometers every day. It will never return. It will never be observed again. Whatever it was, whatever it carried, whatever its story might have been, it is gone. But the questions it left behind are not gone. They are more alive now than they were in 2017. The Vera C. Rubin Observatory is preparing to survey the sky with unprecedented sensitivity, and models predict it will detect interstellar objects at a rate of 1 or more per year. The European Space Agency's Comet Interceptor mission sits ready to be redirected toward an interstellar visitor if one is found in time. Private initiatives and academic groups are designing dedicated interceptor spacecraft, small and fast, capable of reaching objects on hyperbolic trajectories. The theoretical community is producing increasingly sophisticated models of what interstellar objects should look like, how they should behave, and what their diversity tells us about the planetary systems that produced them. The next interstellar object is coming. It might already be inside Jupiter's orbit, drifting inward, too faint to detect yet, but growing brighter as it approaches the Sun. It might be a perfectly ordinary comet, trailing a textbook coma and dust tail, confirming that Oumuamua was an anomaly. Or it might be another anomaly, another object that defies classification, that refuses to fit the categories we have built. If it is, we will be ready in ways we were not ready before. We will see it sooner. We will observe it more thoroughly. We will have hypotheses prepared and instruments calibrated. And we will not be caught flat-footed by the discovery that the galaxy sends us things we did not expect. This is what Oumuamua gave us. Not answers, but the infrastructure of inquiry. Not certainty, but the tools to pursue certainty the next time opportunity arrives. Not proof of alien life, and not proof against it, but a framework for engaging with the question, honestly, rigorously, and without the cultural baggage that has long made the topic untouchable. Some mysteries are solved quickly. A question is asked, data is gathered, a conclusion is reached. Some mysteries take decades, as new instruments and new insights gradually erode the boundaries of the unknown. And some mysteries, the deepest ones, change the way we ask questions rather than providing answers directly. Oumuamua belongs to the third category. It arrived, baffled us, and departed. In doing so, it rearranged the intellectual landscape of planetary science, astrobiology, and the search for extraterrestrial intelligence in ways that will take a generation to fully appreciate. It was not what we thought it was. That statement applies regardless of which hypothesis you favor. If it was a natural object, it was not the kind of natural object anyone had predicted. If it was artificial, it was not the kind of discovery anyone had imagined. In either case, it violated expectations. It broke categories. It forced revisions. That is what the best discoveries do. They do not confirm what we already believe. They expose the limits of what we believed and invite us to think larger. Consider one final scaled comparison, one that puts the entire story in perspective. The Milky Way galaxy is roughly 100,000 light-years across. It contains something like 200 billion stars, each potentially surrounded by its own system of planets, moons, and debris. The interstellar space between those stars, the space that Oumuamua traversed for millions of years before its brief encounter with our Sun, is so vast that if you could somehow shrink the entire galaxy down to the size of the continental United States, every star would be a grain of sand. And between those grains of sand, the distances would still be measured in meters. The emptiness would still be the defining feature. In that America-sized galaxy of sand grains, Oumuamua would be a particle too small to see, a speck of dust drifting between grains, invisible, insignificant, and nothing that happened to drift past one particular grain at one particular moment, only to be noticed by creatures so small that they lived on a mote orbiting that grain. And yet those creatures noticed, they measured, they argued, they built telescopes and wrote equations and launched satellites, and debated fiercely about what this visitor from the dark might mean. They disagreed, sometimes bitterly, but they did not stop looking. They did not stop asking. They turned their confusion into motivation, their ignorance into engines of inquiry, and they began preparing to do better next time. That is the story of Oumuamua. Not a story of answers, but a story of the relentless human need to understand. Not a story about what we found, but about what finding it did to us. It changed the way we look at the sky. It changed the questions we think are worth asking. It changed the instruments we are building, the missions we are planning, the theories we are willing to entertain. A small, dark, tumbling object, barely visible, impossibly strange, passing through our corner of the galaxy for a few weeks before vanishing into the void, managed to rearrange the intellectual furniture of an entire civilization. The title question has an answer, and it is this: Oumuamua was not what we thought it was because we had never thought about anything like it at all. Our categories were built for a solar system that we understood, objects born here, living here, dying here. Oumuamua came from outside those categories. It was the first ambassador from the space between the stars, and it arrived speaking a language we had not learned yet. We are learning it now, slowly, imperfectly, with the humility that comes from realizing how much we still do not know. Right now, as these words reach you, Oumuamua is out there, moving, silent, unlit by any star. It carries no message that we can read. It bears no flag. It represents no nation, no world, no civilization, or perhaps it represents one we will never identify. It is simply an object in motion, governed by the same laws of physics that govern everything else in the universe, continuing a journey that began long before the Earth existed and will continue long after the Earth is gone. Somewhere, far from here, far from any sun, in the absolute cold and absolute dark of interstellar space, it tumbles, end over end, 7 hours per rotation, exactly as it did when it passed us, exactly as it will do for billions of years to come, indifferent to the arguments it caused, indifferent to the telescopes that tracked it, indifferent to the species that noticed it and the questions that species could not answer. It came, it passed, it left, and we are still here, looking up, wondering what it was. The sky does not answer, but we have not stopped asking. And somewhere out there, beyond the reach of light, beyond the reach of any instrument we have built or any spacecraft we have imagined, a small dark object tumbles on, carrying its secrets into the endless night. It does not know what it is. It does not care what we think it might be. It simply moves, onward, outward, into the dark. The first visitor from beyond the stars came and went in silence. The next one will not find us silent. We will be watching. We will be ready. And when it comes, we will finally have the chance to ask the question that Oumuamua made us desperate to answer. What are you?